Mese, a student at University of the Western Cape, South Africa, and I am here today to present to you an ongoing research on assessing the effectiveness of groundwater remediation technology to a coastal aquifer within an urban environment. With increase of climate change and decrease of surface water, groundwater has become a reliable source in many places in the world. However, it has been reported that groundwater has been polluted in many places through natural or anthropogenic ways. In 2018, Winter reported some water-related challenges in terms of water shortage and water pollution in South Africa. Therefore, it is important to remediate such groundwater. Remediation is the process of removing contaminants from polluted water. There are three common methods used in remediating groundwater, and these include physical, chemical, and biological. In this study, we are focusing on the reverse osmosis, which is a physical chemical purification method. The aim of this study is to assess the effectiveness of the technology for improved water security. In order to do that, three objectives have been put in place, and in order to answer the research question, which is, what is the effectiveness of remediation technologies for groundwater contamination, and what is the performance? This is our study area in Cape Town, Western Cape, and we are working on the Cape Flats Aquifer, which is found in the city of Cape Town. The area is divided into two aquifers, the shallow and deep aquifer, and we are working on the shallow aquifer. The area is largely known with undulated sand areas connecting the hard rock of Cape Peninsula. Therefore, the geology of the aquifer is mainly sand, which varies from unconsolidated to semi-consolidated. Reverse osmosis is one of the technologies used to remediate groundwater in coastal areas, and this is also known as a desalination. Reverse osmosis is a partially permeable membrane that removes ions, unwanted molecules, and large particles from drinking water. Water is forced into the membrane and several elements into the vessels, and these membrane layers are thin and are made up of different layers. Membrane remove molecules based on their shape, size, and charge. Contaminants larger than water molecules will not pass through. As the water passes through into the membrane and the clean water is sent into the permeable tube, and the clean water is called desalted water, and the concentrated water is the water that is not clean. On my right hand is a simple technology demonstration that shows the process of reverse osmosis, how it works. At University of Western Cape, we are using reverse osmosis and ultrafiltration in cleaning the water. Water is being pumped from 4 boreholes and is sent into the collection tank. A chemical called caustic is added to break down iron and manganese to increase pH of water. And this water is sent into the cone filter where the activated carbon is present, and these activated carbons help to filter out some chemicals, some contaminants. After that has been done, the water is sent to the ultrafiltration where more contaminants are removed, such as drug, iron, and manganese. 50% of water is then sent to the RO membrane so that it can be sent to the treatment, to the collection tank. The RO membrane is in 3 stages. However, they are all working to remediate groundwater in the same process. It is not advisable to drink this water as it is still under process. After the water has been collected into a collection tank, the water is sent out and is mixed with municipal water. So what we are doing here is to sample water before the remediation to identify contaminants and their concentration levels. And we are going to sample water after the remediation to identify the contaminants level in the technology as well. These are some of the desalination plants that are currently being used around the world, for example, in Israel, South Africa, and China. Results from some studies indicate that reverse osmosis is 97% effective in removing contaminants. A study done by WEFE indicated that it was 95% effective in removing pharmaceuticals in the water. Another study done by SOM found that the technology was 96% effective. Through these studies, we identified an equation that will help us to determine the effectiveness and hoping to find similar results. This is our two equations that we're hoping to use on our project, where removal rate percent is 1 minus A over B times 100, where A refers to a residual fraction of pollution after remediation, and B is the total amount of pollutant before remediation. The second equation is removal efficiency, where CI is a concentration before remediation and CE is the concentration measured after remediation. And we are going to compare our results with different literatures and see if the technology is also effective before the water has been sent out for use on campus, as this water is used for drinking and different purposes on campus. With that, I thank you all.
Thank you so much for that presentation, Jessie. Definitely insightful. If you look at the trend, with climate change for coastal cities, I personally live in Port Elizabeth, so maybe some of that technology can find its way to PE. Bearing in mind the unit costs and the cost of the membranes and so forth. Maybe as you look at the questions, you can also maybe tackle that particular aspect. If we go to the questions, let me see if there are any questions. I don't see any questions. I don't see any questions. But maybe if you allow me from my side, maybe if you can take a look at that particular aspect on the unit costs of the membranes, which will cascade obviously to the cost of the water. If you compare it with municipal water from surface water, if you can please just talk to that.
All right, thank you so much, Kasonde Mlenga.
Go ahead, please, Jessie.
Oh, so the comparison between the water, the surface water and the groundwater, I'm not sure if I got the question correct. Can you please come again, Mlenga?
No, I was basically just talking about the unit costs. How does it measure up at the moment? Is it like prohibitive, or is it something that we can do? Because I know in the Western Cape, there's reverse osmosis. And also I think, is it Knysna as well, one of the coastal towns within the Western Cape as well?
Yes, so Cape Flats Aquifer is part of the coastal aquifer. So remember, the Cape Town is it's within the coastal aquifer. So Cape Flats also falls in the coastal aquifer. So in the long time ago, it was believed that the ocean was kind of at this area, and then the ocean moves on further. So that's why we identified it as a coastal aquifer, because it's closer to the coast. So some of the contaminants that are present that we know about, like salt, iron, and stuff, they're also present on this. However, it is only dominated with iron and manganese in the present area. So the unit cost of that, we can say the surface water is dominantly by salt and sodium.
Thank you so much. If there are no more further questions, maybe we can move to the next presentation by Silas David.
Yes. Yes, Kasonde. I was going to just barge in here. Sorry, can I disturb you, Chair? I think let us say we have a question and answer session at the between 10 and 20 and 10:20. So okay. Perhaps what we can do is just run through the presentations and then we come back and we go to the question and answer sessions later on.
Thank you for the clarification, Chair. Much appreciated. Let's move on to the next presentation by Silas David. The title of the presentation is Production Boreholes, Water Quality Evaluation Using GIS-Based Geostatistical Algorithms in Windhoek. Over to you, Silas. Silas, are you available?
Silas is unfortunately not here. We're waiting for Rakul to join us. If we can perhaps go to Lindelani Lalumbe's presentation, that would be good.
Thank you.
Thank you.
Noted. Let's move on then to Lindelani Lalumbe's presentation. The title of the presentation is Assessing Concentration Level of Contaminants in the Groundwater in the South Pansberg region of South Africa. Over to you, Lindelani.
Okay. Morning, everyone. My name is Lindelani, and I'm a PhD student at the University of the Western Cape, and I also work for the Department of Water and Sanitation. Today, I'll be presenting on assessment of concentration levels of contaminants in groundwater of the South Pansberg regions in South Africa. Next slide. Sorry for this. I'm struggling to get to the next slide. Yeah. Okay. In terms of background, availability of water in general is declining because of climate change and increasing demand owing to socio-economic activities. Globally, it's been reported that groundwater that was considered fresh is increasingly being contaminated or polluted. And this is having a negative impact on the livelihood of vulnerable people relying on groundwater. So the aim of today's presentation will be to establish the type of contaminants in groundwater and assess the concentration levels of these contaminants using the South Pansberg aquifer system as a case study. Then the first objective will be to determine the type of contaminants in the South Pansberg aquifer system. Then also to demonstrate the method used to determine the concentration levels of contaminants. Also to determine the suitability for groundwater for domestic and also for irrigation use. This is the study area. In the study area, there are about 14 geosites consisting of 12 bowls and 2 geothermal springs. And this is an ongoing study. And these geosites are being monitored and managed by the Department of Water and Sanitation as part of their groundwater quality monitoring program. In terms of the method that we use, firstly, for classification of contaminants, common contaminants in groundwater were determined from global, regional, and local literature. 124 samples from 12 bowl and 2 spring, which are geothermal spring, were sampled between 1994 and 2017. In terms of procedure, these bowls were pumped for about 20-25 minutes before sampling. Measurement were also conducted. Samples were analyzed at the laboratory and other anions and cations. When the results were back, ion balance error was conducted for each sample for quality control and assurance. For determining the control level of contaminant, statistical analysis were conducted using Excel. Standard deviation, mean, maximum, and minimum control level of contaminants were determined. For spatial distribution of contaminants, interpolation method on ArcGIS was used in order to determine if these contaminants are affecting groundwater is inside for suitability for use. For drinking purpose, the results were compared with the SANS 241 2015 standard and also with the World Health Organization standard. But the SANS 241 standard was taken, prevailed because it's a local standard. For suitability for irrigation, TDS classification was used. Also, sodium absorption ratio was used. Sodium percentage was used. Permeability index was calculated. Magnesium hazard was calculated. Residual sodium carbonate was also calculated in order to determine suitability for irrigation purpose. When it comes to results, in terms of types and content level of contaminants, it was determined that in rural areas across the world and also in South Africa, the most common contaminants in groundwater are nitrates, EC, fluoride, total coliform, and sulfate in mining areas. These contaminants are resulting from agricultural activity, sanitation issues such as pit artillery in rural area, and also unregulated dumping of waste. In the southbound aquifer system, fluoride, nitrate, and salinity were found to be the major contaminants in groundwater, with, for instance, TDS with a maximum of 1,869, with nitrate with a maximum of 37 milligram per liter, and fluoride with a maximum of 2.9. So in terms of fluoride concentration as a contaminant, where is it concentrated more? In the study area, only in the area, we have a mean fluoride of 2.5 milligram per liter here. This is a geothermal spring. The maximum level of concentration for fluoride here was recorded at 2.9 milligram per liter. In terms of nitrates, 3 areas were identified as being having nitrates, which is high. For instance, at the Maebane area, at the western side of the study area, the mean nitrate of 22.3 milligram per liter was determined. At Gogogo area, ZQM triple G1, 50 milligram per liter was the mean for nitrate, and at Chitawa, Samando, nitrate concentration of 50 milligram per liter was determined. In terms of salinity, also here, like there were 2 areas that where TDS was over 1,000 milligram per liter, which is the ZQMP MA1 in the Pundamaria area next to Kruger National Park, and also in the Maebane area in the western side of the study area. In terms of suitability for drinking purpose, because people here use groundwater without any treatment, they just pump and use groundwater. 91 of the 124 samples, which represent 73.4% of the samples were suitable for drinking purposes, and 9 out of the 14 sites, which are bowl and geothermal spring, are suitable for irrigation. The most common contaminants in the area that's making groundwater not suitable for drinking purpose are TDS, fluoride, and nitrate. In terms of suitability for irrigation, using these 5 methods, the salinity hazard-based methods such as sodium percentage and sodium absorption ratio determine that most samples are between excellent and permissible for irrigation. However, the magnesium-based method, which is the magnesium hazard, show that most samples, about 75.8%, are unstable for irrigation. permeability index method classify them as class 3, where all samples were unsuitable for irrigation. Residual sodium carbonate also put all samples were suitable for irrigation. The most common used method to determine suitability for irrigation is the sodium absorption ratio. So the special distribution of potential for irrigation in the study area is displayed here, where you can see that ZQM TPS2, which is a hot spring at Chipisa, groundwater there is doubtful for irrigation, and also at ZQM PMA1 at Punamaria, at the eastern side of the study area is also doubtful for irrigation. However, majority of the area range between excellent and good for irrigation purposes. In conclusion, these studies conclude that major contaminating groundwater in Oxford-Wansbeck aquifer system are fluoride with a mix of 2.9, nitrate with a mix of 37 milligram per liter, salinity STDS with a mix of 1,869. Again, majority of the samples are suitable for irrigation, and also 9 of the 14 sites are suitable for irrigation. Based on salinity hazard method and residual sodium carbonate, majority of the samples range between excellent and permissible for irrigation. So it is then recommended that which is the next step of this study to determine the potential sources of contaminants, and also to understand the hydrogeochemical processes, control groundwater quality. And also the next step of this study is to determine an appropriate groundwater remediation or technique that can be used to improve groundwater quality in the rural area. Also, groundwater users in areas such as Mayabane, Gogogo, Pundamari, and Titawa, Samando should be cautious when using groundwater for drinking purposes, as the current level of contaminants are above the South African National Standard of 2015. Thank you.
Thank you so much, Lindelani, for that presentation. We'll quickly move on to the next presentation. I've been reliably informed that Raquel Souza is available to do the presentation on the groundwater game, a serious game to foster a shared understanding of sustainable and equitable groundwater management. I'll then hand over to you, Raquel.
Okay, now it's on. I'm sorry for this confusion. Good morning, everyone. My name is Raquel Souza. I work at IGREC, and we are participating in this conference, in this congress, to present to you the groundwater game, a serious game to foster a shared understanding of sustainable and equitable groundwater management. But first, I would like to tell you that the groundwater game was created, the first idea, the first concept based on the tragedy of the commons was created in 2008 among the IGREC team. And since then it has been further developed, the content has been improved, and new features were added along the way. But for those who are not familiar with this serious game, a serious game, by definition or by defined in 2005 by Chen and Michael, is a game that do not have entertainment or food or fun as their primary purpose. So a serious game has a priority, a specific learning purpose, and an added pedagogical value. The groundwater game is set in an Excel calculation sheet. And this year, one of the last improvements of the game was the development of 2 apps, a Windows app and an Android app, facilitating the interface, the game flow, and the interface between the game manager and the players. So right now we just released a Windows app and the Android app where the Excel calculation sheet is connected to the app. And furthermore, this Excel sheet is also connected to a PowerPoint presentation, being the 3 main features and interface of the game. So the Excel calculation, the app, and the PowerPoint presentation. So what is the groundwater game? The groundwater game was developed with the specific objectives of improve the participants' understanding of the function of groundwater systems and introduce technical concepts, foster a deeper appreciation of the collective action choices and challenges for regulating groundwater use by influencing policies and management policies, and finally, to open a discussion on the challenges of sustainable and equitable groundwater resources management. Along the groundwater game and through the game, several concepts and understanding are given directly and indirectly to the players. So concepts has groundwater development, common pool resources, drawdown, surface and groundwater interaction, overuse of groundwater, environmental consequence, development scenarios, regulation, transition costs, and collective actions are concepts worked along the game. And in the end, covering many aspects of groundwater management and also governance. So, but how is this game set? What are the rules and what are the players' roles? Aiming to improve the groundwater management through cooperation and collective action, the game is set within a hypothetical rural community where there are 9 farms. Each farm has 1 hectare, 1 borehole and 1 crop. To irrigate this crop, farmers need to use 1,000 cubic meters of water per hectare per season. The 9 farms, meaning the 9 players, are irrigating their crops from the same aquifer, which is the common source of the game. Furthermore, in the setting, in this hypothetical rural community, there is also one lake hydraulically connected to the aquifer, to the groundwater resource. In this image here, in the right bottom corner, you can see the distribution of the wells, and meaning the farms and the lake in an Excel chart. So, but how can you win the game in this setting? The winner of the game is the farmer or team that has accumulated the most profits and at the end of the game, but without, of course, damaging the common resource nor the environment. The game is developed along 3 scenarios. So 3 scenarios are set, and through the 3 scenarios, the rules changes and the players are given opportunities to make moves and to have a strategy to win the game. So the first scenario is called randomly pumping. The second scenario is called reaching cooperation. And the third scenario is advanced management. Going quickly through the rules of the game, the scenario 1, randomly pumping, starts from a scenario where farmers can abstract water without any rules, without any communication with the neighboring farmings. So each one is on its own. The crop, they have benefits from the crops, they have pumping costs, they have living costs, and they can also have costs if they dry the lake. In the second scenario, they start rich cooperation and they are given opportunities to start communicate among each other. They can invest in water saving equipment and they can set a cap rule limiting the groundwater abstraction among the players. Finally, the third scenario is the advanced management, where a groundwater authority that regulates groundwater abstractions imposes environmental taxes proportional to abstraction, and also players and the farmers contribute to the management, deciding on the limited and the penalty costs to be applied by the authority, the groundwater authority. This game was the first idea, the first concept of this game was set based on the tragedy of the commons, where a common resource is explored by individual, and after a while, without a proper management of natural resources, the collective action can have negative consequence, both for the users of the environment resources, but also for the resources itself. So this game focuses on the collective action in groundwater management, the role of stakeholders in water and users are different. So while stakeholders develop governing arrangements, water and environmental laws, and they participate in the planning process of groundwater use, water end users commit to change their behavior. They follow the rules of governance, but they are actively also engaged in the management of the resource. So finally, and coming to an end, I would like to share with you some of the sessions that were held in sub-Saharan Africa by the project Grow Futures, where this game was used as a stakeholder engagement tool, training and capacity strengthening, and groundwater governance. If you want to know more about the game, please follow our website, and thank you very much for your attention.
Thank you so much, Raquel, for that presentation. Really appreciate. I'll move straight to the next presentation. This will be by Lorica Africana. The title of the presentation will be Evaluation of Temporal and Spatial Variations of Groundwater Quality of the Swakop Upper Omatako Basin in Namibia. Over to you.
Good morning, ladies and gentlemen. My name is Lorica Africana. I'm a postgraduate in Integrated Water Resource Management for Namibia University of Science and Technology, and I'm currently working for Department of Water Affairs. Like it was pointed out, I'm going to present you a research done on evaluation of temporal and spatial variations of groundwater quality of the Swakop Upper Omatako Basin in Namibia. My co-authors are Mr. Liberty Moyo and Ms. Elise Mbandeka from the Ministry of Agriculture, Water and Land Reform. In terms of introduction, in Africa, groundwater degradation is one of the major water resources problems, and water in Namibia is scarce and water supply is unreliable. Surface water is lost, and groundwater is very important source for Namibia. And groundwater pollution may be undetected for many years if groundwater quality is not monitored. Groundwater monitoring is considered very important to understand and identify water quality trends, and also to determine the acceptable water sources. The SADC Groundwater Management Plan, SAM, does monitoring in the Uranium province since 2010, and the monitoring is done once a year. This research was to evaluate the temporal and spatial variations of groundwater quality in the Swakop Upper Omatako Basin. In terms of the study area, the location is the western central part of Namibia. The overall size of the study area is 30,100 square kilometers. The uses of water in the area is domestic, small-scale farming and mining. The urban population in the study area is 380,000, and the average annual rainfall ranges between 0 and 50 millimeters, and the borehole depth is between 9.57 meters and 41.7 meters. The temperature ranges between 10 and 12 degrees Celsius. Okay, I'm just experiencing a bit of a problem. Okay. In terms of methods, 16 boreholes were monitored for groundwater quality. For the monitoring, the SAM groundwater sampling guideline developed by GSN and BGR was used. For the procedure at the site, the water level and depth measurements were done. The boreholes were purged for 20 minutes, and the parameters that were measured in the field were turbidity, temperature, pH, and electrical conductivity. 2 field water quality monitoring kits were used for the monitoring in situ, and the water was collected in a 10-liter bucket to avoid the change in the chemistry. 3 grab samples were collected at each site. The first one was to test for the drinking water quality. The second one was for the trace elements, and then the third one was for the total phosphate. The samples were kept in a fridge for preservation, and the NAM-water laboratories was used for the chemical analysis. In terms of the water quality trends, secondary data from the SEMP monitoring that was done between 2010 and 2016 was used. And in terms of data analysis and processing, descriptive statistic was used. Correlation analysis was used to test for how water quality parameters correlated to the distance of the boreholes. And ANOVA analysis was used to identify statistical significance between concentrations of parameters between sites, between time monitored in 2017 and between the years. Microsoft Excel 2013 was used, as well as Minitab for that statistical analysis. In terms of results and discussion, comparison of the mean concentration to the different standards, it was found that turbidity, electrical conductivity, total dissolved solids, cadmium, lead, and uranium did not conform to any of the standards that it was confirmed to the drinking water quality standards. In terms of water quality survey, although a range of parameters have been measured in this study, only the critical ones will be presented today. I will display the results and show the spatial variations as well as the temporal variations, and give a summarized version of all the results. In terms of temperature, the temperature was measured for years 2012 and 2017, and there is a small variation in temperature with time for the measured boreholes during the 2 years as shown in the figures. According to Kringle, Wagner, and Klinger in 2010, the mean temperature for the boreholes for the study area was 24.8 degrees Celsius. However, the mean temperature of 28 degrees was found during the study period in 2012 and 2017. The temperature difference can be attributed to the general global temperature rise due to climate change. And in terms of pH, the pH ranged from the lowest of 7 in the year 2011 to the highest of 8 in 2013, as shown in the figures. Hamotoko et al. In 2014 found the pH in the study area to be near neutral, ranging between 6.6 and 7.8. However, during the study period, the pH had increased and ranged between 7 to 8. However, the pH conforms to the Namibian water quality guidelines as well as the WHO water quality guidelines. In terms of total nitrogen, the total nitrogen concentrations in the groundwater samples were only measured in 2 seasons in 2017, and there's an increase in the total nitrogen from the wet to the dry season. This can be due to low recharge into the groundwater during the dry season, leading to an increase in the concentration of total nitrogen. The boreholes located in the lower Swakop and also located in the Rosing uranium area should not be used for drinking without bringing it to a required standard. The excessive nitrogen can cause restriction of oxygen transport in the bloodstream, leading to blue baby syndrome in the infants, according to the USE Water Science School in 2017. And in terms of total phosphates, the variable was measured only during the wet and dry seasons of 2017. And during the study in Cape Cod, the geological survey of the US Geological Survey in 2017 have shown with their study that phosphorus migrates in groundwater. The increase in the phosphate during the wet season can be due to the recharge of groundwater from surface water sources. During the wet season in 2017, both the Khan and the Swakop rivers had flooded, which can attribute to the increase in the total phosphates in the wet season. An increase in the total phosphates can be an indication of pollution from untreated sewage or agricultural activities. In terms of turbidity, the concentration of turbidity increased especially from boreholes inlet to boreholes towards the ocean. Turbidity of boreholes range between 0.10 and 194 NTUs. The highest concentration was recorded in the boreholes located close to Kwanekonde's Oasis Rest Camp, where Bannerman Resources was busy with exploration activities and where there were also a lot of vegetation found, followed by a borehole located in the lower Swakop River, as shown in the figures. The high concentration of turbidity can be due to an increase in the TDS in the groundwater, which was measured at 16,999 milligrams per liter in 2017. Most of the boreholes have turbidities below 20. However, the turbidities are above the Namibian drinking water quality guideline, or value of less than 0.5 NTUs. In terms of total dissolved solids, the TDS varies from one season to the other. However, the trend in the boreholes almost remained the same. The concentrations measured increase as the boreholes move towards the ocean. According to the US Geological Survey in 2017, mixing of freshwater and seawater in the aquifers along the coast can occur. The increase in variables towards the coast can be due to this factor, and the concentrations of TDS does not conform to any of the water quality standards. Treatments by processes such as desalination of reverse osmosis are recommended to lower the TDS. In terms of arsenic, the arsenic levels have been constant for all boreholes for the year 2012 and 2014. However, in 2017, results showed a marked increase in the arsenic concentrations in most of the boreholes. When compared to the study done by Kringeltham in 2010, there is an increase in the concentration of arsenic in the study area. The major land use activity in the study area is mining of uranium. The probable cause of the increase in the arsenic concentration can be due to the mining or to the geological formations. The mean arsenic concentration for the study area is 0.01 milligrams per liter, which conforms to the Namibian and WHO drinking water quality guidelines. In terms of uranium, the uranium concentrations vary from season to season within the individual boreholes, and it also varies spatially as indicated in the figures. Of the two other similar studies done in the study area, the ranges indicate that there is an increase in the concentration of uranium in the study area. Uranium is one of the minerals that is found naturally in the rock formations of the study area. This can, however, be due to the geology of the study area. During their study, Kringle et al. In 2010 found that 6 boreholes in the vicinity of Rossing uranium mine and Langerheinrich mine had elevated concentrations of uranium at 0.23 milligrams per liter. The mean concentration of all boreholes for the study period is 0.09 milligrams per liter, which does not conform to the Namibian or the WHO water quality guidelines for drinking water. In terms of the statistical analysis, correlating water quality parameters, the pH is inversely correlated to the EC and TDS. The temperature is correlated to the EC and TDS, and temperature is correlated inversely to the arsenic at a strong confidence level of 83%. EC is positively correlated to the TDS, as was expected at 99%. The EC and TDS also positively correlate to the arsenic. However, the correlation confidence levels are different. In terms of correlation between the water quality parameters and distance between boreholes yearly, the results show that the position of the boreholes along the river does not have a statistically significant effect on the groundwater quality. All the water quality parameters did not show any correlation to the distance in the sampling period. For the ANOVA analysis, from the ANOVA analysis done between sampling years, it was found that 4 out of the 11 parameters measured rejected the null hypothesis that there is no significant difference in the groundwater quality temporally. And for turbidity, electrical conductivity, TDS, total nitrates, and uranium, there is no significant difference in the groundwater quality during the wet and dry seasons of 2017. And in conclusion, the water quality indicates that the groundwater is not suitable for drinking without treatment. 4 out of the 11 water quality parameters indicated that there is a statistically significant difference in the concentrations throughout the study period. And between the boreholes, the study found that there is a statistically significant difference in temperature, EC, TDS, total nitrogen, and uranium concentrations. There is significant difference in water quality. For some parameters with space and time, it can be due to factors like pollution. Certain parameters are high at certain boreholes and not at others. And an increase in the concentration of arsenic, lead, and temperature were found in the study compared to the previous studies done. And boreholes found downstream or in the vicinity of mining had elevated levels of arsenic and uranium, although when statistically tested, they were found to have no significant difference. In terms of recommendations, it is recommended from the study that water from boreholes should be treated before it is used for domestic purposes, and an increase in the arsenic and uranium concentration were found in this research. It is recommended that more research be done on the pollution source of parameters, and radioactivity and radon could not be monitored, and it is recommended that for future research, the parameters be monitored if possible. And for this research, 37 references were used in total. And with that, I would like to thank you for your attention. Thanks.
Thank you so much for your presentation, Lorica. We appreciate. Looking at the time, we will then move on to the question and answer session. We'll open it up. Moving on to the question and answer session. Kindly post your questions in the Q&A box for the presenters to respond. I know some questions were posted already and then they received answers. But if there are any more questions to the presentations that we've had, kindly post your questions so that we can get the answers from the presenters. Are there any questions, colleagues?
Sorry, Chair. There is a question in the chat box, not in the Q&A box, but in the chat box. It goes to Lorica. It says, now that the water is not suitable for drinking, what is it being used for as of now?
Okay. Lorica?
Can I respond?
Please do.
Yeah.
Okay, so most of the land use activities in the study area is mining. So most of the mines are using the water for cleaning the mine and in their production. So it's not really used for domestic purposes because we only have a few small scale farms around there in the study area. I hope that answers the question.
Thank you for that. There was a question from Jesse talking about the presentation on the desalination in the Western Cape. The question reads, is your desalination process, you said, takes up 50% of water in the RO. What happens to the other 50%?
Hello, so to answer Kwazi, the other 50% is the water that is blended from the ultrafiltration. So the 50% remains with the ultrafiltration and the only 50% is sent to RO so that the water, the RO is not pressurized or it's not put into too much force. So 50% is left in the ultrafiltration and the other 50% is the one that is sent to the RO for the processing.
Okay. Thank you for that clarification. There was another question from Demisani. As presented, the foundational principles in the groundwater game appears generic of any water source or resource. Where there is competition in use, why is specifically branded groundwater game?
Hello, everyone. Yes, as I already answered in the questions box, I didn't have time to go through the details of the game, but the calculation sheet simulates an aquifer, and along the game, players' moves are related to the amount of water explored within the wells. After the exploration and depending on the volume of water explored, calculations of the drawdown are made. And the lake and the boreholes are hydraulically connected. So yes, this specific game is specific for groundwater use, although of course it covers concepts related to the integrated water management resources. But the calculations are based in the TIES equation and specific for groundwater.
Thank you, Raquel. There's another question from Christy to Lindelani. Says, hi Lindelani, just checking on the criteria used to select the parameters for your study. Some of the contamination sources identified in your study would suggest the possibility of heavy metals, some more nutrients apart from N, as well as other emerging contaminants. Was there any consideration on this? The question is to Lindelani.
It seems as if he's not with us, Chair.
He's not available.
Can I, Mr. Kasonde?
Yeah, please go ahead.
There is a question in the chat box from Mr. James for me. Okay. He's asking the temperature range between the 10 and the 12 degrees of the project. Was that during the time of the project or in the general? Okay, in the general range of that area. I would like to answer that the range, that the 10 and the 12 degrees was found from literature, and it's actually the atmospheric temperature that I was talking about there. But during our research, the range that we found of the groundwater was between 23.8 degrees and 30.5 degrees. That was for the groundwater, but then the 10 to 15 was for the atmospheric temperature that I gave from the literature that we found.
Thank you for chipping. I see Lindelani is available. Lindelani, did you get the question? Should I read it?
Yes. Like, is the question about like what criteria was used?
Correct, yes.
Okay. Basically, currently we use our own data. So when we go to a site, that's when we check what more parameter can we add to the existing one. For instance, the data that we have, it doesn't have biological parameters. It just only it's only like a physiochemical parameters. So we haven't actually sampled our own parameters so far.
Okay. Thank you for that, Lindelani. I hope that has answered Christy's. I hope, Christy, you're satisfied with that answer. Are there any other questions, points of clarifications, colleagues? We are slightly ahead of time, so we've got ample time for more questions if concerning the presentations that were just done in this session. I'm looking to see if there are any other questions that are being generated.
If I may?
Go ahead, Raquel.
Yeah, there's a couple of questions and maybe I can summarize a general answer for everyone. So the groundwater game is available for downloads. So anyone can actually play the game. It was made available with a manual, with the apps, with all the tools needed to anyone in anywhere can play the game. Right now with this COVID situation, it can also be played online. Also, the game was released under copyrights that allowed anyone to further develop, change, adapt the game as long as the credits are given to YGREC and the new versions are released under the same licenses. And final. The reason why we developed the apps in 2020 with the support of Grow Future project was because of the positive feedback on the sessions held during the Grow Future projects in some countries in sub-Saharan Africa. So if we are planning to play the game in other African countries, we don't have a plan. We did release the game so that anyone can use this tool anywhere, and we are of course available to help in sessions, being it online or presential. But of course, this costs, it has costs associated. That's why we tried to release this version so that anyone can play it without being dependent on YGREC. I think this answers to most of the questions that were posed related to the groundwater game.
Thank you for that, Raquel. So when it's downloadable, are you talking about the online platforms like on your Android and?
Yes, the Excel file, the PowerPoint, the two apps, they are available for download in our site. I already shared the link in the chat and questions, the chat questions and answers. So the Excel calculation, which can be changed and adapt. The two apps can be downloaded from Google Play and for Windows and Android. You have a manual also with, well, we try to make it as good as possible. Of course, any feedback is welcome. And so it's set to be played. In our site, you have the whole set of the game, yes.
Thank you for that. There's a question from Mr. James Aramba. Is the game available in other languages?
Not yet, James. No, not yet. No.
Okay. Any plans to make it available?
Not for now. We are always depending. The development of the game is always depending on further funding. So that's why we now release it to other people to be able to adapt it or develop it. So next steps and next further developments or translations are depending on funding right now.
Thank you so much. Obviously, it's generated quite some interest. So I think it.
I'm very happy, and we will be very happy to share further information or support sessions if you want to hold it in universities, with the governments, with the stakeholders. We can always support.
Thank you so much.
Thank you.
Okay. Are there any other questions, colleagues, concerning the other presentations that we've had during the session? I don't see any questions, any other questions. Maybe I should rope in the session chair. Micah, just your direction. Should we go for break right now so that we bring the sessions forward?
Yes, thank you very much, Kasonde, for chairing this session. I think the presentations have been good, and because of one presentation that has not come in, we are ahead of time. I would suggest that we take the comfort break now, and let's see, what time is it now? It's 9:42. Maybe we reconvene at 10 o'clock, hoping that the next presenters will be available to start the program again at 10. So that would be my suggestion.
Yeah, no, thank you.
Okay, so thank you so much. If there are no further questions, I would like to, unfortunately with the virtual conference, we can't clap for you. Nobody will see the hands clapping. So, but I would like to thank you so much, Kasonde and James Manda, who has been doing the rapporteuring for this session. It has been very exciting, you know, and very educative. You know, we've talked about things on water quality, climate change, so, and how it is affecting groundwater. So this is really good. It has been a good session. So thank you so much. So colleagues, I think what we're going to do now is we break for a comfort break and we reconvene at 10. Thank you so much. Hello, colleagues. Welcome back. It's 10 o'clock now. We had announced that we would like to reconvene at 10. Can I just make maybe one announcement that don't forget, you know, to tag us on our social media using the hashtag GW Conference for 2020. And we are also on Twitter and Instagram at SADC-GMI and also on Facebook. So let us continue to engage colleagues, you know, as we go through our program for the second day. And I just wanted also to make an announcement that we are trying not to go ahead of most of the presenters. And we have decided that perhaps, you know, we give extend the comfort break to 10 past 10. And whilst we are doing that, you know, there will be some videos being played so that you can also familiarize yourself with you know, some information about the conference. And also, colleagues, don't forget to register, to fill in the register for today, because we would like to know, you know, who attended the conference, you know, for the second day. So we urge you to look at that registration form and please kindly fill it in. I'm going to go off a little bit now until 10 past, you know, and we'll rejoin at 10 past and enjoy the videos that will come through with some information on the conference. Thank you very much, colleagues. We reconvene at 10 past 10, and we'll continue with the program. Thank you.
Welcome to the SADC Groundwater Information Portal, a web-based tool for sharing groundwater data and information in the SADC region. It is accessible at www.sadc-gip.org. In this SADC GIP, you can access several map layers in a catalog. There are layers on aquifers, groundwater recharge, boreholes, transboundary groundwater resources, groundwater drought risk, and many other topics. Several filters are available to help you find the right layer. Each layer can be visualized in a map viewer, and if authorized by the data provider, you can even download the data and metadata. The SADC-GIP also contains maps which are made of several layers and documents like PDF, Excel, or images. Just like data layers, also maps and documents can be accessed and filtered in catalogs. Anyone can register for the SADC-GIP. As a registered user, you get additional functionalities like uploading data, accessing restricted data, creating maps, and joining user groups. When creating your account, please provide information about yourself to facilitate interaction with other users. Whenever you upload data to the SADC-GIP, you decide which users or user groups can visualize, download, or edit it. Therefore, you always user groups can visualize, download, or edit it. Therefore, you always remain in control of your own data. Make sure to fill in the metadata fields properly to let other users find your data and use it properly. Additional restrictions and licenses can be assigned to the metadata. The SADC-GIP provides all professionals and organizations a secure and flexible environment for sharing groundwater data and information among themselves as well as with the public. The main goal is to enable all of us to participate in an informed manner in the sustainable management of vital groundwater resources of Southern Africa. You want to know more about the SADC-GIP? You can find more information in the GIP manual or contact us through gip@sadc-gmi.org.
The council area and its boundaries, their water level is very low. And as you are aware, in Zambia, 2018, 2019, rainfall patterns changed drastically. This project, it is intending to move water from a community that is about 27 kilometers away to come and give service to the community at the end of the 27 kilometers away.
Groundwater has always played a very important role, particularly for drinking water supply. As we know, particularly in the continent in Africa, thousands of boreholes have always been drilled to provide water for people, particularly at this centralized level, where you don't have surface water that is of acceptable quality. Normally you try to drill a hole and try to find better quality water.
And I provided land, space for boreholes to be drilled. These workers will be doing the work for the entire community in the district.
With the help of this project, we did a lot of investigations, detailed investigations. So we did not just go in to start drilling. We had to do some detailed geophysical surveys. From our assessment and investigations, we have seen that that is a well field. All the parameters are showing that that's a well field.
I've seen the project progress. I think it's really the results of a vision that integrated water resources management has to be pursued to achieve sustainable water access and use.
I'm very grateful that I have been chosen in Chongwe, part of my chiefdom, for this service to come.
Mais uma vez, bom dia. Meu nome é Nádia Chambal, estudante do curso de Engenharia Hidráulica, Agrícola e Água Rural, no Instituto Superior Politécnico de Gaza, em Moçambique. O meu estudo trata do seguinte tema: avaliação dos processos hidroquímicos e da qualidade da água subterrânea no leito seco do Rio Limpopo para irrigação agrícola em Macaretânia. O estudo foi feito em Moçambique. Como introdução, as águas subterrâneas, comparativamente com as águas superficiais, apresentam melhor condição natural. Entretanto, devido à sua diversidade litológica e à variabilidade química nela presente, podem apresentar modificações nas suas cargas contaminantes. As águas em zonas semiáridas, onde a fonte hídrica superficial tem tido problema exatamente na época seca do ano, as águas subterrâneas são tidas como alternativa para dar continuidade com a produção agrícola na época de escassez das águas da fonte hídrica superficial. O presente estudo visa trazer informação do leito que ocorre no leito seco do Rio Limpopo e foi feito na zona sul de Moçambique, concretamente na província de Gaza, distrito de Chokwe, no posto administrativo de Macaretânia. Como objetivo geral, tem o seguinte: avaliar os processos hidroquímicos e a qualidade da água subterrânea no leito seco do Rio Limpopo, em Macaretânia. 3 objetivos específicos foram determinados. O primeiro é determinação dos parâmetros físico-químicos da água subterrânea e superficial, identificação dos processos e fases hidroquímicas na água subterrânea, determinação da classe de qualidade de água para irrigação. Problema: existem estudos que já foram feitos que comprovam a boa qualidade da água subterrânea que ocorre no leito seco do Rio Limpopo. Existem também estudos que comprovam a boa quantidade da água subterrânea que naquele lugar existe. Porém, desconhece-se a variabilidade da qualidade da água daquele local. O desconhecimento da informação da variabilidade da qualidade da água do leito seco do Rio Limpopo pode trazer problemas futuros se a mesma for usada para irrigar as culturas, sendo que a mesma pode não apresentar os mesmos padrões de qualidade de água durante as 2 épocas hidrológicas. Esse estudo vem trazer informações relacionadas com a hidroquímica da água, de modo que a mesma água seja usada para garantir o crescimento socioeconômico e a segurança alimentar. O trabalho foi feito na zona sul de Moçambique, concretamente na província de Gaza, no distrito de Chokwe, posto administrativo de Macaretânia. O posto administrativo de Macaretânia, ou o distrito de Chokwe, é caracterizado como apresenta uma precipitação de 600 milímetros por ano. Tem um clima característico de zonas semiáridas. Apresenta uma média de temperatura igual a 26 graus Celsius. E a evapotranspiração é de 1.500 milímetros por ano e é caracterizado com solos ou com argilas vermelhas. A principal atividade socioeconômica desse distrito é a agricultura. A coleta de dados foi realizada no dia 24 de novembro de 2019. Durante um período de 4 meses, foi feito monitoria no campo para determinar-se o grau de mineralização através do condutivímetro e o nível do lençol freático através da sonda elétrica. Duas metodologias foram usadas para a determinação dos parâmetros físico-químicos da água subterrânea, o método laboratorial e o método in situ, ou o método do campo. O método in situ foi acompanhado por monitorias do campo, em que usaram-se sensores portáteis para avaliar o pH, a condutividade elétrica e a temperatura. No método laboratorial, foram usadas duas metodologias para a determinação dos parâmetros físico-químicos que existem na água. O método ICP para a determinação dos cátions e o método IC para a determinação dos ânions. Os métodos gráficos, o diagrama de Piper, o diagrama de Stiff, assim como a correlação iônica, foram usadas para identificar as fases e processos hidroquímicos que existem na água subterrânea. Foi também usada a metodologia proposta pela USSL para a determinação das classes de qualidade de água para irrigação. Essa metodologia é feita através de dois parâmetros, a condutividade elétrica e a razão de sódio dissolvido. Os resultados referentes aos parâmetros físico-químicos da água subterrânea mostram que todos os íons, 100%, todos os íons apresentam-se 100% nos intervalos da água usada para irrigação, segundo vários autores que encontram-se citados na última coluna direita da tabela. A correlação foi feita com base na classificação de Pearson. A classificação de Pearson permite classificar a correlação sobre três formas. Os valores iguais a 0,41 e não superiores a 0,61 são classificados ou apresentam uma correlação moderada. Os valores iguais a 0,61 e não superiores a 0,96 apresentam uma forte correlação. Os valores iguais a 0,96 a 1 apresentam uma correlação muito forte. A terceira forma foi usada nesse estudo, a correlação muito forte. Para o nosso caso, ou por acaso dos resultados que aqui obtidos, encontramos que existe uma forte correlação, ou uma correlação muito forte dos íons condutividade elétrica, magnésio, bicarbonato e sulfato com os outros íons como o magnésio, a TDS, o bicarbonato e o sódio. A forte correlação desses íons pode ser explicada pelo fato de a água que ocorre neste local pode estar associada com um tipo de mineração de sedimentos geológicos por onde a água flui e do equilíbrio resultante da interação química. Os processos hidroquímicos foram determinados com base nos cálculos do cloroalcalínico 1 e 2. Os resultados referentes aos cálculos feitos com base nas duas equações do cloroalcalínico 1 e 2 são todos eles negativos. Segundo Laxman, Nakarashi e os outros autores, valores negativos indicam que existe uma troca iônica dos íons cálcio, magnésio e sódio, e são esses íons que controlam a qualidade de água neste local. Foram também identificados dois intemperismos presentes nas duas fontes de água, isso é, na fonte subterrânea, assim como também na fonte superficial. Os resultados que encontram-se acima da linha simétrica indicam o intemperismo de carbonatos e abaixo da linha simétrica indicam o intemperismo de silicatos. Para as amostras das águas subterrâneas foi identificado o intemperismo de carbonatos e para as amostras das águas superficiais foi determinado o intemperismo de silicatos. As fases hidroquímicas foram determinadas com base no diagrama de Piper. O diagrama de Piper é composto por dois triângulos e um losango. Os dois triângulos, ou o triângulo que encontra-se à esquerda, representa os cátions, o triângulo. A combinação dos ânions e dos cátions é projetada no losango central, e é no losango central que iremos encontrar a tipologia da água. Para o caso das nossas amostras, ou para o caso das amostras de água por mim feita, a água foi classificada como sendo de tipo bicarbonatada, cálcico ou magnesiano. Foi também determinado as situações que existem nessa água subterrânea. Aqui temos resultados das duas fontes de água. As três figuras acima representam a fonte de água superficial e as quatro outras figuras abaixo apresentam o tipo de água, a fonte hídrica subterrânea. Existe uma afeição
Okay, it looks like we've got a connection problem with Nadia. It will allow her to rejoin. Nadia, can you hear us?
Desculpar-me.
Okay, she's back. Thank you. Okay, please share your presentation again. We lost you there.
Sim, gostaria de desculpar-me. Primeiramente, tive queda de internet. Sim, eu explicava acerca das fases hidroquímicas presentes na água. Foram usados o diagrama de Steve para determinar-se a concentração dos íons ou o comportamento dos íons na fonte hídrica. Existe uma afeição geométrica das duas fontes de água, isso é, o íon bicarbonato encontra-se maior concentrado tanto na fonte hídrica superficial, assim como também na fonte hídrica subterrânea. Os resultados, ou esse resultado, pode indicar-nos a interação dessas duas fontes de água, isso é, a fonte de água superficial serve ou pode servir de recarga da fonte de água subterrânea, mas também os poços com maior concentração do cálcio, assim como também maior concentração de bicarbonato, indicam um maior grau de calcita, resultados de maior tempo de armazenamento no aquífero e maior profundidade de armazenamento dessa água. Foi também usado o método para determinação da classe de água através do diagrama proposto pela USHL. Mas antes calculou-se a razão de absorção de sódio. Todos os resultados das amostras de água indicam que a razão de absorção de sódio é menor a 10 miliequivalentes por litro. Resultados de razão de absorção de sódio menores a 10 miliequivalentes por litro indicam uma boa água ou uma adequada água que pode ser usada para irrigar os campos sem riscos de deixar o campo sódico. Foram também determinadas duas classes na água, C2S1 e a classe C3S1. A classe C2S1 é caracterizada de sodicidade e um baixo nível de salinidade. E a classe C3S1 é caracterizada por apresentar um alto nível de salinidade e um baixo nível de sodicidade desculpe, cometi um lapso. Na classe C2, S1, eu queria dizer que é caracterizada por apresentar um médio nível de salinidade e um baixo nível de sodicidade. A classe C3, S1 é caracterizada como apresentando um alto nível de salinidade e um baixo nível de sodicidade. Tanto a classe C2, S1, assim como a classe C3, S1, pode sim ser usada para irrigação, mas com pequenas restrições para a classe C3, S1. Deve ser usada para solos que tenham uma boa drenagem, para não ser prejudicial ao uso desse solo. Os resultados referentes à determinação dos parâmetros físico-químicos da água subterrânea, referentes à identificação dos parâmetros identificação dos processos e fases hidroquímicas, como é o caso do intemperismo de carbonatos, intemperismo de silicatos e a troca iônica dos íons cálcio, magnésio e sódio, revelam que a água subterrânea que ocorre no leito seco de Rio Limpopo é boa para irrigação ou pode ser usada para irrigar os campos na época de escassez da fonte hídrica superficial, e a mesma não apresenta variabilidade da sua qualidade durante o período seco do ano. E muito obrigada.
Okay, thank you very much. Nadia, you may follow at least the presentation. May I, Nadia, can you hear me? You may stop sharing the presentation.
Yes.
Okay, thank you. So please turn off your video so that we don't have any buffering challenges. Right. So participants are allowed now to perhaps place their questions on the Q&A tab at the bottom there, so that Nadia can respond to them within the session. However, we'll go to the next presenter. According to the schedule that I have, Ndumbisi, I hope I pronounced that correctly, who will talk about using hydrogeophysics and derivatives analysis of improved groundwater security for Western Cape. I believe this is from University of Western Cape. So please share your presentation, thank you, and then put it in presentation mode.
Good morning, can you hear me?
Yeah, yes, we can hear you.
The
video is of poor quality, we can see.
Okay, let me just stop it and go on presentation mode. Just 1 minute. Just 1 minute is coming up now. Okay, can you see my slide?
Yes, we can see it. Presentation mode now.
All right. Just coming up now. I don't know why it's not coming up. Please just give me a minute. Okay, is it up now on your side? And can you hear me clearly?
We can hear you loud and clear. Please present.
Okay. All right, good morning. My name is Ndubisi from University of the Western Cape. Today I'm talking on using hydrogeophysics and derivative analysis for improved groundwater security using the Western Cape of South Africa as a case study. there's a need to improve groundwater security, especially in urban areas where the demand for groundwater as an alternative source of water supply increases. Also, the decline in the availability of surface water due to climate change also make these a critical issue. And because of this, there's also a much more need to understand the aquifer system in terms of the groundwater storage and also in terms of the yield, which traditionally is being interpreted using the time drawdown plot. Now, most hydrogeologists still interpret some cases of pumping test data using still matching with the theoretical curve type that is obtained from the THEIS 1935 and the Copper and Jacob method. And by regularly fitting these curves, they come up with an assumption that pumping tests produce cylindrical radial flow regime, and thereby ignoring the actual flow regime that is occurring within the aquifer. And the use of curve fitting only does not show the practical heterogeneity of aquifer flow dynamics. And that's why we're employing the use of derivative analysis or derivative plot, which addresses such weakness by amplifying the real heterogeneities in the aquifer system. Now, the literature informing my study includes Salmani et al. In 2006, where they used derivative analysis to characterize a heterogeneous aquifer. Renard in 2009 also used the diagnostic plot method for well test interpretation. And lastly, my key article, Ferrod et al. 2019, they used the diagnostic plot method, and they specifically recommended that an integration with hydrogeophysics is important. Now, this is the study framework. The problem here is that the use of hydrogeophysics and derivative analysis in modeling groundwater flow system remains poorly understood and explored. And that leads us to the research question that says, what are the advantages or the influences of using hydrogeophysics and derivative analysis in groundwater modeling, either in conceptual or numerical modeling or both? And the argument here is that when hydrogeophysics data and derivative analysis are not used in groundwater modeling, it results in over-idealization of our models, and it makes it impossible to realistically represent the real complexity that exists within this aquifer. And to answer this question, we set up 3 objectives. Firstly is to establish the groundwater unit using the electrical resistivity tomography, ERT, and also estimate our aquifer parameters. Secondly, the determination of the aquifer flow regime using derivative analysis, specifically the diagnostic plot method. And thirdly, to demonstrate the influence of hydrogeophysics data and derivative analysis in groundwater modeling. And the overall aim of the study is to demonstrate the advantages or the influences of hydrogeophysics data and derivative analysis in pumping test interpretation and groundwater conceptual flow models. Now, this is my study area. The study area is in the West Coast District Municipality of South Africa. It is in the Berg River catchment, and geologically it is composed of semi to unconsolidated Cenozoic sediment of the Sandville group. Now, aquifer system can be grouped under lower aquifer unit and the upper aquifer unit, but my study is mainly focused on in the lower aquifer unit, which is around the G10M here, and made up of 2 main aquifer units, the Langerburn Road aquifer unit and the Elandsfontein aquifer unit. Now, talking about the method, we have 2 figures here. Figure 2A is an example of a resistivity and normalized changeability interpretation, and the 2B is the theoretical flow regimes and their associated flow dimension. Now, the figure 2A, which is the resistivity survey, is a typo of what we are actually doing, because this is an ongoing study currently happening, where we will first put up our resistivity flow, resistivity line. Secondly, the normalized changeability will show. And thirdly, the hydrogeological interpretation, where we would define each of the layers that is being seen during the survey. And the second figure there is the theoretical flow regime, where we can be able to interpret each signature of the derivative sequentially as the pumping tests go on. Now, you might ask, why is derivative analysis important? Now, derivative analysis is a powerful diagnostic tool that enhances the interpretation of pumping tests. Features that are difficult to discern using the traditional time drawdown plots are often apparent when we use derivative. They become amplified. Okay, in 2018, Ferrod, he reassessed 121 interpreted flow regime, and he found that amongst the 121 interpreted flow regime, 69% of those flow regime were actually non-radial, but they have been interpreted using the traditional time drawdown curve and assumed that they are actually radial. And again, studies have found from field investigation that flow regimes occurring in real media are actually more complex and diversified than what is being modeled. Now, as we can see from our figure 3B here, showing a realistical example of what I'm saying, where you could see at early times here, the unit slope here on both the drawdown and the drawdown derivative versus time indicates a well-born storage. As we can see here, it moves also from one medium to another, where we can see a slope here indicating a possible spherical flow. Okay, and here we can see it changes again from one medium to the other. Okay, where we can see a radial flow here. And the dotted lines we can see here, the dotted lines you can see here are the change in aquifer from one aquifer unit to the other aquifer unit, or from one medium to the other. And that is what derivative analysis do. It amplifies the heterogeneity that occurs in this aquifer system. It makes them much more better for us to see and interpret. Now, from our preliminary findings, we've been able to see that the application of derivative plot is very essential in determining the correct model that can be applied to a set of time drawdown curve. And we see that derivative analysis or derivative plots are more suited to uncover heterogeneity that occurs in aquifer system. The boundary conditions, as you can see from my previous figure that I showed, it tells the boundary conditions from one aquifer unit to the other aquifer unit. The boundary will be very significant and apparent when we use derivative plot. And again, the various flow regime that occurs during the pumping cycle sequentially will be shown when we employ derivative plot. And again, the inclusion of hydrogeophysics data and the use of derivative analysis leads to a much more better understanding of the groundwater flow regime, thereby making our model output more practical for practitioners. Now, in conclusion, we'll be able to see that there are complexities of aquifer that exist in nature, and hence we recommend that most of the assumptions of analytical solution need to be tested not only with the traditional time drawdown plot, but with the drawdown plus derivative versus time plot. And because several conceptual models will produce the same type of derivative, which is actually one of the weakness of the derivative method, we're employing the hydrogeophysical method as recommended by Ferrod in 2018. And this is mainly needed to first understand the aquifer unit, and it helps to annotate the non-unicity of this derivative signal. And thirdly, we've been able to conclude that when we use hydrogeophysical data and derivative analysis, is very, very critical for groundwater models if this model are to inform feasible measures that improve groundwater security. Now, the take-home message from my presentation is that derivative plots are more suited to do four main things. Firstly, they are used to uncover or encounter aquifer boundaries during the pumping test. Secondly, they are used to visualize or amplify the heterogeneity that occurs in the local aquifer characteristics. Thirdly, they are used to uncover various flow regimes that also encounter sequentially as the pumping test is going on. And lastly, they are used in the facilitation of an appropriate aquifer model. Thank you.
Okay, thank you. May I encourage attendees to please post questions in the Q&A. The panelists are not able to do that. Only attendees can post questions. Okay, so we'll go on to the next presenter. Thank you so much to the presenter. The next presentation, this is coming from Lindilani. I've got that. talking about groundwater quality status in South Africa for SDGs 6.3.2, a case study of Free State province. Please go ahead. Thank you.
Hello, everyone. Again, my name is Rinirani, and today I'll be presenting on the groundwater quality status of South Africa, SDG 6.3.2 reporting, and we will be using Free State province as a case study. And I'm from the Department of Water and Sanitation in South Africa, and my co-author is Peter Ramusia. Goal 6 of the SDG talks about ensuring availability and sustainable management of water and sanitation for all. When it comes to target 6.3, it's about to improve water quality by reducing pollution, eliminating dumping, and minimizing release of hazardous chemicals and materials, halving the proportion of untreated wastewater, and increasing recycling and safe reuse globally by 2030. Then indicator 6.3.2, which this the presentation it's about proportion of bodies of water that comply with the water quality objective. In case of South Africa, we set a specific hydrogeological region value. The sub-indicator will be pH, nitrate, sulfate, and EC. A methodology was developed basically to provide a report on how we are going to report groundwater quality for SDG 6.3.2. Firstly, we determine baseline and the targets and the compliance computation. In terms of data source, the National Groundwater Quality Monitoring Program was used where the groundwater samples are collected twice a year, before and after the rainfall season, and is managed by DWS. In total, in the whole country, South Africa, there are about 379 active stations that include bowls and springs. Then reporting aggregation will be the factor 2001 hydrogeological region, as the closest available hydrogeological mapping in the country. Then the aim of this presentation will be like to test the methodology for reporting the current groundwater data in South Africa, and then to check the compliance to the determined target in South Africa using Free State province as a case study, as it has the latest data. Site description, this is the map of the Free State, where we have got 9 hydrogeological regions and 20 groundwater quality sites with data from 1994 until 2020. And these are the 9 regions, which are Central Highveld, Central Fenbelt, Eastern Highveld, Eastern Upper Karoo, Northern Highland, Northeastern Fenbelt, until Southern Highveld. In terms of the method that we use, the method that we are testing, if this method can be used to report for SDGs 6.3.2 groundwater quality site. First of all, statistical analysis approach was applied in developing the methodology in order to develop baseline, target, and compliance. The percentiles were determined at each regions, where the 90th percentile calculation for all available records were considered to be baseline or background groundwater quality, using the long-term data 1994 to 2016 as baseline. This was done for each parameter, EC, pH, nitrate, and sulfate. The target that we will have used here was the draft 1996 water quality guidelines, or 10% range from the baseline. That's only where the baseline is greater than the water quality guidelines. Any fluctuation by 10% from the baseline shows a non-compliance for this for nitrate, sulfate, and EC, while a range was developed, the upper value and the lower value for pH. In terms of hydrological region compliance, we'll say a region is complying if all parameters are complying to the target. Then meaning we say we have 100% compliance. Then the formula used is this formula where HR compliance equals to number of region compliant divided by total number of parameters. In this case, 34 parameters. Then for country compliance, we say the target that will see the country is compliant to be 80% based on this formula, where country compliance will be equal to number of hydrological regions that are compliant over total number of hydrological regions, which we have 65. In terms of the results, we'll start with EC. EC, we will compare the targets and the baseline with data from 2017 and data from 2020. As you can see here, all data, all regions in 2017 and 2020 are all below the baseline and also below the target, meaning we don't have issues with EC in this province based on the methodology that we have applied. Just that in 2017 in the Central Plan Belt, EC was at 300, but there's an increase in 2020 data to about 360, then, which is something that as a department we need to note and see where it is going with more data coming. In terms of nitrates, basically all region but one is not in 2020 is not complying to the target. This is the northeastern Pan Belt, where the EC, when the nitrate value basically doubled between 2017 and 2020. You can see in 2017 analysis, the nitrate was at 30 milligram per liter, and 2020 said 26 milligram per liter, making this region not complying to the set target. Then when you move to pH, basically in pH with the upper limit and the lower limit, all samples in 2017 and also in 2028 were within the range that were set. So in terms of compliance, is pH, we don't have any issue with pH in this region based on the data that we have for 2017 and 2020. When you go to sulfate, the targets for all was 200 milligram per liter, which we use the water quality objective, meaning all the baseline was way below the water quality objective. When we come to sulfate in the Eastern Upper Karoo, in the 2017 data, sulfate was not complying in that area. Also, in the Northeastern Upper Karoo, the 2017 data, sulfate was complying. However, with the latest data in 2020, we noted that sulfate is no longer complying in this area, in the Northeastern Upper Karoo. So, in overall, when you check hydrogeological region compliance for this method, when you apply the formula that we computed, we found that in the region like Central Highveld, there was compliance in 2017 and there's still compliance in 2020. However, regions such as the Northeastern Pan Belt, in 2017 we had 100% compliance. Then in 2020 we have like 75 compliance, meaning one parameter is not complying, one parameter is above the target. Even in the North Upper Karoo, we've got in 2017 we had 100% compliance with the target, but again in 2020 one parameter was not complying to the target that we set based on the formula that we actually used. However, in conclusion, we can conclude that the analysis showed that the methodology can be used for reporting in terms of SDG 6.3.2, meaning we can able to trace the problem area. For instance, in an area where nitrate was not compliant, we can be able to identify the area or a geosite where it's making that region not comply. In terms of compliance, again, within the study area, some regions were complying 2017 data analysis and are not complying to the set target. And this is due to elevated nitrate, sulfate, and EC in the area. Also, some regions show some improvement from 2017 data, 2020 analysis. Parameters such as nitrate, sulfate, and EC in some regions show that the concentration actually went down. Nitrate concentration in the Northeastern Pan Belt is concerning as it's down between 2017 and 2020. So as the department following this methodology, there will be a need for us to analyze individual geosites to see which site is actually making that region not to comply to the set target. Also, sulfate concentration in the Northeastern Belt, Northeastern Upper Karoo and Eastern Upper Karoo is concerning. And also as a department, there's a need for us to actually zoom in and find which boreholes are making a sulfate not to comply in that specific region. So all in all, this method seems like we are confident that we can use this method to report for SDG 6.3.2 for the whole country. Thank you.
Okay, thank you, Lindani, for that presentation. May I encourage our participants and both attendees and panelists to please post some questions. Please post some questions. I don't seem to have any questions in my Q&A. Let's post those questions. The next presenter is Area and Development Community Region. May I invite her to please share the presentation? Thank you. Marina, are you there?
Yes. Sorry, I was just busy unmuting myself here and finding the presentation. Are you presenting or do I present from my side?
Please present from your side. Thank you.
Good. Please confirm if you can see my screen yet.
Not yet.
Yet. You see it now?
Yes, please put it in presentation mode and then you can start the presentation.
Thank you very much. Thank you, everybody. I am presenting something that is not as hardcore as the hydrogeologics or the remediation details that were presented this morning. We're looking more at resources, development priorities, and priority areas that specifically relate to vulnerable populations across the SADC region. And it's been a long journey, and although I am presenting, you will see on the agenda, there's a number of people who participated in this study. So I don't want to take all the glory. Please make sure that when you look at the agenda, you'll see all the names of the participating persons and institutions. So basically the presentation is going to be looking at challenges, working towards interventions in how we can change the lives of people on the ground in vulnerable areas. And my specific focus is number 3, which is one of the components of our study, which is the identification of vulnerable populations. And how do we identify vulnerable populations in an area as big and wide as SADC? And a brief overview of the road ahead, because just identifying populations is not the end. So to start off with, just one slide on the challenges. I think we all know the challenges: crop failures, food insecurity, food shortages, famine epidemics. And you can see here the number of food insecure people per country. It's really staggering. And this was the premise on which this project was started. So working towards interventions, it is important to identify areas that are prone to groundwater drought. And in these areas, assess the water resources that we can mobilize to support sustainable water supply investments. Then we bring in the role of groundwater, especially looking at the surface water supply, the groundwater, and the population management side. So the whole project consisted of 4 key activities, of which only one I am presenting today. If you would like to know more, I'm sure that the SADC-GMI will be welcome to share some of this after the project is finished. So we are looking specifically on how we collected data and how we analyzed data to identify population vulnerability. So going into how we identify the vulnerable populations in such a large area as SADC. The 3 components: mapping of surface water availability and the mapping of groundwater availability and groundwater drought risk, are two separate items, and actually the presentation hereafter, which is going to present, is going to look at what you see here in the green block, which is the evaluation of the groundwater drought risk map. So we are focusing on the one small component, and then the key outcome of this whole project is, as you can see in the blue at the bottom, identification of domestic water supply interventions and being able to identify financial and institutional activities that investors can look towards to implement. So first, before we start, it is important that I just share with you a few terminologies, because I am going to use terminology that may not be known to everyone. The first is when I speak about a polygon, you will see a polygon is an area, and in the top right corner, you would see a polygon being an area. Vectors are points, lines, and polygons. So vectors being points, lines, and polygons. Then we have a model that takes a vector and may present it like raster, or the raster itself is maybe satellite imagery. So as you can see, the vectors and rasters may represent similar outcomes or similar features on the Earth, but in two different ways. Then spatial data layers. When I talk about a layer, I talk about a layer of, for instance, villages or rivers or population density, and we all overlay them to make a map. Then features within a spatial layer means that there is a feature such as a river or a dam that have attributes, and every set of features would have a set of attributes. And this is a core part of the analysis we did in this project, is that we use these attributes that you can see an example of on the bottom left-hand side to present the data and to multiply, animate, and overlay the layers. So to start with our method, first, and I think you've already seen where we're going with this, we collected data. Then after collection of the data, we went into the layers and the features, and we did layer ranking and feature weighting. Then the multi-criteria assessment, where we had a specialist group survey, was done, and we then calibrated the GIS. After that, there was a big GIS component, which is geographic overlays and buffering and weighting and ranking. So it was a very technical GIS component. And finally, we also had a stakeholder engagement process to make sure that we cross-correlate what stakeholders in the region has found in the past. So as you can see, we've had a data component, a multi-criteria assessment component, geographic information systems, and then the review. So I will be identifying each of these 4 items shortly hereafter. When we look at data, it's often a misnomer that data is easily accessible for the whole of SADC. And what we have found in our research is that when we go through the data sets, a lot of the data may not be entirely complete across the whole of SADC. Furthermore, the scale of data is not the same in the region. Some countries or regions have more detailed data and others more high-level data. The vintage or age of the data is really problematic in some areas, especially areas as you go up towards the north of SADC. The vintage is really problematic because it's old data. Then I spoke about regional representation, formatting of the data may not always be in the same format, but luckily these days it's a little bit easier to work with. The challenge is that some of the reports in the region only have maps or data layers in JPEG or PDF format, and it's not in GIS format, which is a challenge. Then the big data, we did need some significant computer power to work with it. And finally, working across an area such as SADC, the projection of these data sets is quite important. Something that really was a necessity to look into and which affected our research is that the island states have a lack of data. The scale of the data and the levels of detail, as well as actual data sets, simply sometimes does not exist. So there's really a data scarcity in the islands. I am not going to go through all of these data sets. It's just a representation of the amount of data sets that we used. And all of these data sets were layered and weighted and ranked, and ultimately provided us with a map that showed the priority areas for community vulnerability. So this layer and ranking and feature weighting process that I've been speaking about consisted of first ranking the layers. So you take one layer and you rank it, and layers may have the same rank. So you may have a river layer that may have exactly the same rank as maybe a livestock density layer, or they may have different layers, and we rank them from maybe more important to least important in terms of identifying population vulnerability. Then we weighted the features within these layers, and same as with the ranking of layers, we assigned weightings and we did a spatial analysis. Now, it's important these two are very separate processes. You weight a feature in a layer and then you rank the layers against each other. So our multi-criteria assessment used a specialist group survey. We went to 10 respondents that are really knowledgeable in various areas as it relates to population vulnerability and groundwater drought and surface water drought. They did not all have exactly the same background or the same knowledge. We then presented them with questions and they ranked and weighted the features. When these questionnaires came back to us, we removed the outlier values, the ones that were like really out there that kind of doesn't fit into the mold. We revisited some of the results and then applied the mean or the average of the values for both the ranking and the weighting. And thereafter we mapped it, we visualized each layer and sense checked the outcome to make sure it really makes sense. So the GIS component, we made all points and lines into polygons, we buffered the lines, we made sure that everything was in polygon format in the end. And then we converted everything to raster, which is a cell size. We then prioritized the layers and allocated their prioritization, summated them, so we overlaid them and then summated them, then sense checked it, and finally identified vulnerable populations. Our sense checking process looked at a variety of data sets across SADC, and this variety include seasonal performance drought trends, for example, as you can see here. We also then did the stakeholder engagement process, and it really involved a number of people at national levels, regional experts, in-country experts, and also finance institutions, because ultimately they are the ones that we would like to go to present some of our interventions to get financed. So the outcomes, and just before we end off, the outcomes obviously is an overlay of multiple layers. So what you see here is not just one layer that causes the outcome, it's multiple layers, about I think 15 to 18 layers that causes this outcome. It means that there is not just one reason why a hotspot is a hotspot. So as you see here, I'm just going to go a little bit in detail, is we then drew ellipses and circles around the areas that are these priority areas. So you can see the areas in dark black or dark red are the actual priority areas. And please note, we know that there are local drought conditions that have been occurring maybe in the past 4 or 5 years. Remember, these data sets are regional and they are long historical trend data sets as well. So please make sure that when you look at this, this does not mean that there are not local pressures. Then finally, each area also has a unique narrative. Narrative meaning a piece of text that describes why the area is a priority area and why the populations here are intensely vulnerable or more vulnerable than in other areas. The island states, as I spoke about earlier on, Comoros, Mauritius, and Seychelles, they in particular presented much lower values because they didn't have data. There was just no data layers. So these island states we re-visualized and changed the color schemes so that you can actually see the hotspots on the islands. So you cannot, in our research, evaluate the mainland with the island states. The two, although the color you see here might be similar, the actual values of those overlays are not exactly the same because the layers don't have as many features and there's not as many layers available. Then our road ahead. So we obviously take this population vulnerability assessment, we overlay it with the groundwater drought risk map, which you'll hear about after now, and the surface water drought risk. So we integrate these three and then identify cost-effective and locally suited intervention options. And these are then translated into investment opportunities. So our aim is ultimately to be able to go to a funding agency or a development partner and present this to them and say, here are things that can be investigated for feasibility or pre-feasibility studies. So we've already decluttered the investment and intervention outcomes. So finally, I'm not going to go into too much detail on this, but what you see in front of you is the integration, the overlay of the population vulnerability with the groundwater drought risk, with the surface water drought risk. And each of these also, there are of course some in the islands as well, I'm just showing you the mainlands here, but each of these also has a narrative that explains why these are then the hotspots. So, muito obrigada, merci beaucoup, and thank you very much. I am done, and I thank you for this opportunity. Thank you very much.
Thank you very much, Marina, for the presentation. We'll come back to you with some questions. For now, may I request that you unshare your screen?
Yeah, if I can just get it done here. Sorry, the technology is, that's better?
Yes, that's better, thank you. Thank you. Our last presenter for the session is Chadza, who will be talking about revising the groundwater drought risk map, the role of GRACE data in mapping groundwater drought in Southern African Development Community. May I invite him to share his presentation? Thank you.
My talk this morning is on the revision of the groundwater drought risk map, especially the role of GRACE satellite data sets in mapping groundwater drought in the SADC region. As my colleague Marina has stated, this was part of a larger project that looked at developing priority interventions in the SADC region. So the creation of the groundwater drought risk the algorithm was developed in 2011 by Vilhoth et al. When they produced the first SADC groundwater drought risk map. Now the definition of groundwater drought risk was looking at the different aspects that make up risk. For the purposes of this discussion, the elements indicated in dark blue, I will call them modules, the ones in gray sub-modules, and light gray at the bottom sub-modules. So the groundwater drought risk was defined as comprising the physical groundwater drought risk, as well as the human groundwater drought vulnerability. So in our efforts to incorporate GRACE data, what we have done is to create a second sub-module called the groundwater storage sensitivity, where we've included three parameters that we derive from the GRACE groundwater drought indices that would then fit into the groundwater drought risk. Now, in terms of the physical groundwater drought risk, it was defined to comprise climate sensitivity and hydrogeological drought proneness. And there was another aspect, which was the consideration of groundwater threats to create a groundwater insecurity map that was outside the scope of the project. So we didn't analyze that. And the elements, what are called sub-modules in light blue, are basically where the data goes in to make up the sub-modules and then the modules. The reason why they adopted the modular approach was because of the scarcity of data in the region. You could essentially calculate one aspect of drought risk. If you don't have, for example, the human, the data making up human groundwater drought vulnerability, you could still come up with a physical groundwater drought risk map. The rest of the presentation will be taking you through the data sets that we looked at when we revised the drought risk map. So the process used is a GIS composite mapping method, like what Marina discussed in the previous presentation, where each parameter is represented by a raster map, each with its own unit. Now the challenge is taking all these maps and converting them into the same unit. So all the vector data was converted to raster, and the raster data were left in their native formats and resolutions. Now to get them all in the same units, the data sets were classified into ranges and then assigned a value from 1 to 5, with 1 being very low risk and 5 being very high risk. The layers are then multiplied by assigned weights and added to create a final map constituting either a submodule or a module. Generally, the most influential layers are assigned higher weights. Now, most of the weighting that we used is based on the study of Vilholt in 2011. So we didn't change much of the parameters, except we did some sensitivity analysis in other cases that indicated to us that the weighting methods were appropriate. In terms of meteorological drought risk, what is considered is basically the mapping of dry areas in the region, and the definition of dry areas, which is based on the World Meteorological Organization, is the rainfall amount at a certain area or cell should be, if it's less than 1 millimeter a day, then the area is classified as dry. If the consecutive dry days in one calendar year are greater than 120 days, that's a dry region. And if you look at the long-term time series and you have dry days for more than 270 days, then that is also a dry area. The other parameters looked at is the coefficient of variation, where the higher the values, the more variable the rainfall in that area, therefore the higher the risk. And the data sets that were used is the 5-kilometer resolution data from the CHIPS version 2 data for the years averaged over the years from 1981 to 2019. So what I've shown at the bottom in red is basically the weighting that was applied to the different parameters, with the rainfall amount getting the highest weight, followed by the standard coefficient of variation. And then lastly, the consecutive dry days are all weighed equally. So the map that is shown is the outcome, which shows the dry areas which have very high meteorological drought risk in red, and then the low, very low risk areas in blue. In terms of the hydrogeological drought proneness, there are two variables that we use, which is the SADC aquifer productivity map, which consists of aquifer storage capacity and permeability. Now, if you had a more detailed data set or a more localized study, you could separate this into two, but because this is a regional study and the way the map was compiled, we determined that it was appropriate to use. So the basic premise is a deeper, extensive, and more productive aquifer would then be less drought vulnerable than a shallow one. The second one is the groundwater recharge potential. Now, because there are no available regional groundwater recharge potential maps, the idea is to use parameters such as rainfall, vegetation, and slope to create a groundwater recharge potential map, with areas of high recharge be classified as less vulnerable to drought. Now, in this case, the rainfall was weighed higher than the two other parameters, which is vegetation and slope, with the equation shown in red. And basically these two, the aquifer productivity and the groundwater recharge potential, were then combined together with equal weights to create the hydrogeological drought proneness map, which is shown with colors ranging from dark blue to a reddish brownish color, with the reddish brownish color indicate areas that are a very high drought proneness. So combining the climate sensitivity and the hydrogeological drought proneness then would give us the physical groundwater drought risk map, which is shown on the slide, with high risk areas shown in red and the low risk areas in blue. So essentially, if you didn't have the other data sets for the other parameters, then you could use this as a representation of physical groundwater drought risk. So we went further and included the human groundwater drought vulnerability study, where we used the population, livestock, and irrigation density, where the higher densities indicate higher drought vulnerability. We also incorporated the perennial rivers, where the higher vulnerability areas are the ones which are the furthest from the rivers. In terms of the data sets, we had the freely available data sets, including the gridded population of the world version 4, the global map of irrigated areas version 5 of 2010, and the FAO livestock data of 2018. So these 4 parameters were then combined in equal proportion to create a human groundwater drought vulnerability map, which is shown with colors ranging from dark blue to red being very high vulnerability. Now, in terms of GRACE data, so the GRACE satellites provide a product that represents monthly changes in terrestrial water storage. Now, the processing steps involve extracting the groundwater storage signal, because the GRACE data comprises different other sources of moisture, including soil moisture, canopy water storage, and snow water storage, and surface water bodies. So after we have extracted the groundwater storage, which we call GWS, we then calculated the GRACE groundwater drought index based on the following formula. So the groundwater storage deviation is basically the difference between the monthly mean and the GRACE groundwater storage data. And then the normalized storage deviation gives us the GGDI. Now, this is a research project being done by my colleague, Zaid. So I'm sure he'll take you into more detail with the more involved mathematics in the calculations. So there were 3 parameters that were derived. So the first one was the percentage of time series in a groundwater storage drought, which we related to the duration of groundwater storage in deficit. The second one was the mean negative GGDI, which shows the mean intensity of groundwater storage deficit. And lastly, the trend of GGDI, which indicates trends in groundwater storage deficit conditions. Now, what is important to realize is the GRACE data is a time series data set. That's why we can derive certain parameters as the trend, because we are looking at a time series. Now, the last processing was refining the resolution, because this is a global data set at 110 kilometer spatial resolution. We had to refine it to the resolution of our rainfall data sets, which were 5 kilometers using linear interpolation. Now, the 3 parameters were then combined in more or less equal proportion to create what we're calling a storage sensitivity map, where areas in blue, dark blue, are very low risk, and areas in red are very high risk. There's also importance of validation, especially when you are using these global data sets and trying to bring it to local original level. An example is the use of groundwater level changes and correlating that with the GRACE groundwater storage signal data. And the results showed that there's predominantly negative correlation and differences in trends between the levels and the GWS. We also went ahead and correlated the groundwater level indicators that we calculated and then with the GGDI, and we also saw some positive correlations and similar trends between the groundwater levels and GGDI. Now, what is important to note is that GRACE data is at a more regional scale, so it's not expected to resolve groundwater levels, which are at a local scale. So that's why you have low to moderate correlation coefficients, but that doesn't mean that there is no correlation between the data sets. So what we did eventually then, we combined the physical groundwater drought risk, the groundwater storage sensitivity, and the human groundwater drought vulnerability to develop the groundwater drought risk map, which is shown on the slide, with areas of high risk shown in red and areas of low risk shown in blue. So the pattern we got is similar to the map of 2011, but of course there would be such differences in the values because of the different data sets and also the incorporation of the GRACE data. But what we found is the areas of high risk are persistent in both maps. In conclusion, what I highlighted earlier was sometimes the challenge is the decision on which weighing mechanism to use or which are the best ways to use for the different parameters. So what we did was carry out a few scenarios and created a coefficient of variation map, which represents the uncertainty and shows areas which are mostly affected by weight changes. And in this study, these areas were very low drought risk areas. So we were confident that regardless of the weighing regime, the high risk areas would still be picked up under any condition. We also looked at how to verify these products because for example, the drought risk map is based on sort of like a GIS-based computer model. So how do you tie it into ground truth data? So we looked at the use of the SPI index to correlate that with groundwater levels and to use it to explain the groundwater drought. So what we show is that in dry areas, the groundwater levels decline for long periods of time before recovery. So this finding was also found by others, for example, Cuthbert et al. They came to the same conclusions. So we didn't do a thorough analysis, which we recommend for future, but the results look promising. What we showed is that GRACE data can be used in mapping groundwater storage across SADC, and through the use of GGDI, the number of parameters that were defined to describe the sensitivity to storage were very useful in groundwater drought risk characterization. I will conclude by saying this is a regional map. So the good thing with the GREENS algorithm is for more detailed catchment scale studies, you can then use more accurate data sets and hopefully refine the map that I've just presented to you. I thank you all for your attention.
Okay, thank you so much, Chetzi. We're now going to go into our Q&A session. I have at least in my Q&A version, I only have one question, and this is from Mara. It says, what does the population vulnerability indicate? Maybe you can just explain that a bit.
Yeah, thank you. The population vulnerability, I see the question is particularly related to Namibia. Now we know that Namibia is in general much more sparsely populated than other areas. For instance, if you look at Tanzania and Malawi, just as an example. So the challenge there is that the population density and the population distribution really drives the vulnerability priority in this case. So in our areas that we looked at as highly vulnerable from a population vulnerability perspective, Namibia did not really pop up extremely high. You will see that there is a zone there that is identified as a population vulnerability and ultimately an intervention hotspot. But the most important part is to remember that even if you now drill down into Namibia, you can use the data to identify even more hotspots in Namibia. And the circle that you see there, I think it was on the last map, the hotspot map, which is the overlay of the groundwater drought risk with the surface water drought risk with the population vulnerability. I think that's the one that you might be referring to. And that is the urban areas around the coast. And there's a number of reasons. I mean, I don't want to go into the details, but there's a number of reasons why those areas are more vulnerable than others. So I don't know if that answers it, because yeah, I'm not sure if the question can maybe be more detailed, or does that answer it?
Yeah, I think from my end, that should suffice, unless the person who posed the question perhaps wants more explanation. But whilst I still have you online, Marina, I wanted also to ask on the multi-criteria analysis, the MCA approach that you used. I mean, what guided it, and what exactly was involved? Was it a kind of a fuzzy analysis that you did, or it's a kind of you know, maybe explain from your approach? Thank you.
Okay, excuse me. So the multi-criteria assessment, obviously there's many types of multi-criteria assessments. The one that we veered towards is called the analytical hierarchy process, where basically you let people evaluate things in relation to each other. So it was a quantitative process in that it was numerical. So the specialists were requested to give numerical numbers to the various rankings and weightings. But in terms of the actual analytical hierarchy process, it is in the end also qualitative, because it is a reflection of somebody's informed perception. So if I say informed perception, you must know these are people who has been working in the region for a very long time. So it's semi-quantitative, whereas it's numerical, and then qualitative because it is actually part of a perception analysis. And I'm not going to go into the analytical hierarchy process now, but that was the type of multi-criteria assessment we did. Does that answer your question?
Yes, yes. Thank you so much. Thank you so much. I had also another question for Nadia, who was talking of this evaluation of water quality, looking more on the processes that affect this dry bed aquifer in Limpopo. Was there any assessment that was done towards the quantity of water available, besides just the quality? Thank you. Nadia, are you there?
Yes, I'm here. Sim, estou aqui. Poderias, por favor, repetir a questão?
Okay, maybe she can just type the response if it's difficult to respond. Okay. Okay, then another question on the derivative analysis. I think there was somebody from University of Western Cape, if I remember. So the derivative analysis, according to your presentation, is a requirement perhaps to improve perhaps how we perhaps model these aquifers in terms of boundary conditions and what sort of conditions perhaps in which this aquifer is sitting. Could you explain what the role of ERT, because you did show some geophysics ERT measurements there, and the derivative analysis, was it more to justify that there are other boundary conditions and refinements that go into perhaps unraveling the properties of this particular aquifer. Thank you.
Thank you, Kawawa. Can you hear me?
Yes, I can hear you clearly. Thank you. Go ahead.
Okay, so the role of the geophysics, there are majorly two. Okay, firstly, I'm seeing Nadia. I don't know if she's speaking. Hello?
Okay, Nadia, maybe you can type your response in the chat. Thank you.
Okay, can I go on?
Yes, please go ahead.
Okay, so I said the role of geophysics in...
Gostaria que escrevessem a questão, estou com problemas de perceber a questão.
I don't know if I'm to speak because I'm still hearing Nadia.
Okay.
Hello.
Okay, thank you. So Nadia, my question was to do with the quantities of the aquifer. So what sort of groundwater, what sort of quantities are you seeing in this aquifer? You've explained on the quality that there is presence of magnesium, which is basically coming from geogenic processes. But can we know something about the quantity available so that we know that it's sufficient to meet the demand in terms of perhaps when you get challenges of climate? Thank you. So whilst Nadia is responding, UWC.
Yes, I can hear you. I can hear you. Can I speak now?
Please go ahead.
Okay, so I said the major role of geophysics there is two things. Firstly, to understand the aquifer units under study. Okay, that is number one. Then secondly, one of the weakness of the derivative method is the non-unicity, whereby several derivative signature produce a same conceptual type of model. Now, in the study of Ferrod et al. In 2018, they recommended that a hydrogeophysical investigation should be introduced in the derivative study, that it helps to annotate the non-unicity of the derivative, meaning that when we do an extra geophysics investigation before we do derivative, we tend to have a better idea of the aquifer system first before we do derivative, before we go for our derivative analysis. So firstly is to understand the aquifer under study, and secondly to annotate the non-unicity of the derivative signal.
Okay, thank you. So just in very clear and simple words, are we saying that the current approaches in then characterizing our aquifers are underestimating or overestimating? What then is your feeling on this?
No, in simple terms, what I'm saying is there are advantages when we use the derivative method. There are advantages. Of course, the traditional method, which is being used currently, has been helping, has been in use for a long time. But I'm just saying there are better influences and advantages when we use the derivative signal in terms of amplification of the heterogeneity of the aquifer system. That is just the direct message.
Okay, I see. So this is more on the aspect of characterization, describing it, so it being put in the context of a model that we can capture all these different boundary conditions in a more accurate manner.
Yeah.
Okay, excellent. Thank you.
Thank you.
And another question for Lindani on this reporting framework that you are proposing. There are other reporting frameworks that are being used, have been proposed by, I think, different committees for SDG reporting. What is new with the methodology you're proposing? Did you try to compare with existing protocols that are being used at the moment?
Yes. Can you hear me?
Yes, I can hear you.
Oh, okay. What's new is like we divided this thing into hydrogeological regions, and also like we actually wanted to develop our own baseline using long-term data, and we didn't want to use water quality standard for drinking purposes and all, because we wanted to, because according to our understanding, the baseline should be like the ambient groundwater quality. So we didn't find anything that was talking about the ambient groundwater quality. For instance, in some area, our data from 1996 to 2016 maybe show that nitrate in that area is like around 50. We took that 50 as a baseline. We didn't compare to any drinking water standard in that case. So I think that was like what different from other framework.
Okay. So what then was the source of some sort of a desired water quality parameter? Was it based on some sort of guidelines, South African guidelines? I'm not sure I heard that clearly.
Like I didn't hear your question well.
Okay, so in terms of the target, because you had, for instance, you had nitrate, and you said compared to perhaps a previous reporting cycle, there was some sort of difference with nitrates. So what, are you using the previous reporting as a baseline, or it is being compared to some sort of a guideline or a standard that is available?
Oh, okay.
What is the source of this? Is this a South African guideline? Is it a World Health Organization guideline?
Okay. What happened at first? The first option was to do the 90th percentile statistical analysis on the data that we have from 1994 until 2016. Then, in case where the target was determined to be like 10% range from the 90th percentile. Then, in cases where the target it's lower than the water quality guideline of Department of Water and Sanitation of 1996. That's where we took it as a baseline. We took it as a target. So basically, the first option was to develop the baseline based on the available data, not at any standard. We incorporated the water quality guidelines of 1996 after determining the baseline from the data that we had.
Okay, excellent. That is noted. All right. A question for Chedzi and Zaid on the chat. It says, what are the differences in the approach used in the application of GRACE data sets in this regional study and the one reported yesterday for the Ramotswa, and what informed the difference in the approach?
Thank you for the question. I think I would like to refer that to my colleague Zaid, because he's involved in the other study and I'm not sure if he's available to take the question.
Okay, Zaid, are you online? I can see him online here.
Good morning, Chair. Am I audible?
We can hear you loud and clear. Over to you.
Okay. Thank you very much. The raw data for both GRACE data sets in the previous project and this one were the same, but the post processing was different. So In that case, we just use the Grace groundwater storage for the Remostwa. And in this, the Grace, the groundwater drought map now for SADC, the Grace data was converted to the Grace groundwater drought index, which is two different parameters at the end of the day. One was the pure Grace groundwater storage, and in this case, in what Chicha presented, was the Grace groundwater drought index that was developed by Thomas et al. 2017. But essentially, the raw data is the same. It's just pre-processed or post-processed into different parameters. I hope that answers the question, at least.
Yeah, I think that is clear, at least from my end. Just another question also, Zaid, whilst we still have you online. Grace obviously is quite coarse in the way that it captures these dynamics for groundwater storage. Did you attempt to perhaps do some, in situ validation of, this data, besides you just taking it off, given the amount of errors and the cleaning up that you had to do?
No, definitely. I think Chicha did present on the validation of the Grace groundwater storage parameter and how we attempted to correlate it with in situ groundwater levels. Obviously, we need to understand that the Grace data is homogenized in the sense that it's averaged. The raw data is averaged across let's say a 300 kilometer square grid, and that average is not expected to resolve your local groundwater conditions. More realistic would be to average the groundwater levels at the same resolution that the Grace data is at, and then see what type of correlations you would get. But obviously, we don't have the level of data to do that in reality in many parts of SADC. And this is why we are attempting to, or that's why we see sometimes poor correlations between the groundwater level, the in-situ groundwater levels and the Grace groundwater storage. So yes, we definitely did look at the validation of the data sets for the Grace data. But in conclusion, yes, some of it is poor, but there are some cases where the groundwater storage has a good correlation with groundwater levels.
Yeah, so the only validation, at least, which we saw from Ched's presentation was with the SPI, if I'm not mistaken. So this SPI versus what is coming out from the Grace data. Was there any in situ? I'm not sure I saw that.
No, there was. You did demonstrate the slide that they have the title validation, and that validation was for in situ groundwater levels. Where you saw the histograms of the various colorations. And there was another slide that did demonstrate the SPI in terms of validation, but we did do both.
Okay, excellent. Okay, thank you for that clarification. Just back to Marina. I see that you present two maps. One which had this very nice plot, which you called sort of a consolidated map, which has the population risk, the surface water risk, as well as I think the groundwater, and I think also the groundwater risk aspects. There are certain areas, at least from, maybe if you can share that presentation so that I can refer. Yes. Yeah, so there's this one which you do show, which you said there's a population vulnerability aspect, and then you showed an earlier one of this inland, the mainland area. Yes, this one. So what is the difference between these two maps? Because from what I see, there are certain, of course, there are certain areas which are not highlighted here, which are highlighted in the other one.
Yes. Okay. So what you see on your screen currently is only population vulnerability. So it disregards groundwater risk and to a large extent surface water risk, because obviously some of the population vulnerability details does include things like how far people might live from a river or from a water source. So what you see in this one is purely population-based, population density, population distribution, livestock intensity, distance from how far people live from water sources, and basically it's just focusing on population. Excuse me. When you then go and you overlay on top of this the groundwater drought risk and the surface water drought risk. Now remember, the groundwater drought risk specifically looks at groundwater, as Chitsa has presented. Then the surface water, that one we haven't presented yet, but it looks specifically as where there's surface water risks. Now, let's say for an example, I'm going to take an area between Angola and the DRC. You see there's a small hotspot in population vulnerability between the DRC and Angola. Can you see that like almost in the top center there? When you now go to the overlay, you will see that that area is, as an example, not identified as a hotspot after the overlay and integration of groundwater drought risk and surface water and population was done. And one of the reasons for that is, for example, that the rainfall there is much higher and the groundwater risk in that area, specifically as an example, is much lower. So it makes the population there not as vulnerable as maybe in other areas. So what you see here is not just population. It really looks at the way that the groundwater and surface water drought risk impacts the population. Does that answer the question?
Yes, thank you. Again, curiously, because I live for instance, in Zambia, right? And part of that has been highlighted, part of the area you've highlighted is where we live, and in Lusaka, that is. And I can see very clearly that what you're suggesting is that the area is vulnerable towards, of course, the groundwater aspect, because we are very dependent of at least 60 to 70% of the water in Lusaka is coming from this aquifer system, not so much on the surface water part. So I think it makes sense then to have these kinds of maps here. Okay, thank you, Marina. I don't see any questions, comments from panelists. So I'm just going to pick out one or two people who I can see. I can see Dr. Sumaya from University of Western Cape. Do you have any specific question to the panelists? Okay, so maybe she's stepped out from where she's sitting, or at least has connection problems. Brighton, do you have any questions, anything that you want to point out, perhaps?
Thank you, Kawawa. Maybe mine is just a small question to Zahid. Is it Zahid? Around the issue of GRACE datasets and their applications to groundwater, especially in the region where we have a serious lack of monitoring data. And I've seen that the discourses around this issue normally revolve around the downscaling from the coast scale to a local scale. What would you maybe recommend in terms of downscaling approaches? I've seen there are quite different approaches that can be used depending on the conditions and the local conditions and the availability of data from different platforms. What would you think probably works best for our region. And my concern is we are getting a lot of these investigations being done, and from your experiences in the Ramotswa and this regional study, what would you think is probably the best approach and what precautions need to be taken? Thank you.
So yes, thank you very much for the question. The downscaling of the GRACE data has been an ongoing investigation for us in our research and in some of our projects, not just including this GDR map, but in other projects as well. I guess there are quite a few approaches, and we've experimented with a few of them to try and resolve the GRACE data at the more local level, or to define the resolution that is of the GRACE data. The challenge that we face is perhaps that we still need a lot of local data on the ground in order to validate, or at least to ensure that when we do our downscaling and we perform our predictions on a local scale, that it's valid, at least on the local scale, and that's one challenge that we have, is that when we do our downscaling and we try to resolve this, we don't know the accuracy of our data because we don't have these the local data sets. We did it in this project, and we couldn't really say for sure that the results were correct or not, simply because we didn't have the spatial distribution of groundwater levels to compare to the GRACE data. Now, groundwater levels in itself is not perhaps not the correct parameter to use in relation to the groundwater storage that you're getting from GRACE. It's more relevant to use in situ groundwater storage values to compare the GRACE data to, and that is even less available than the GRACE than the groundwater levels data. So there are opportunities to look at the resolution and to attempt to downscale the GRACE data, but we're going to need a lot more data, at least from our perspective, to do the work. I hope that answers the question as well.
Yeah, yes, it does. And I'm also happy that you've also raised one issue that I've been trying to put my head around, that relates to the concept of the water level as obtained in the in situ data, and that the GRACE data sets will give us changes in storages, and how do you move from one to the other, and especially in a data scarce region like ours. But I think I'm satisfied with the response. It's okay, thank you.
Maybe I can just comment on that as well. We've experimented quite extensively with the machine learning aspects of downscaling, and there's a lot of potential in the machine learning to do the downscaling. It seems to be a very straightforward method compared to your more advanced numerical models, and it's something we're going to look forward to into the future. But as you said, there's still some work to be done on the ground as well.
Thank you, Zaid.
Excellent, Zaid. Whilst again we still have you, Dr. Sumai actually posted on the chat trying to find out what sort of error margins are involved when downscaling and what risks then that comes with. And is this defined in terms of volumes of water available, to the potential users?
So just on the last point of volume, so GRACE data won't give you absolute volumes of groundwater or terrestrial water in that matter. It's the difference between observations that it can give you. So it's the difference in volume. So you can calculate the difference in groundwater storage between the observations, in this case the monthly observations, but it can't give you the absolute volume of a particular aquifer or a region. So that's one of the limitations of the GRACE data in its raw form. in terms of error margins, obviously compared to the local groundwater storage, some of the literature, at least that we've been following, has some decent or at least good results. But we are lacking at least the groundwater level data on the ground, like I said, in order to ascertain these accuracies between the Grace groundwater storage and the local data. Yesterday's presentation that I presented on our downscaling approach in the Ramotswa aquifer, we had an error of 17 centimeters on average in calculating the groundwater levels from Grace data, Grace groundwater storage. So if you want a reference, at least as I'd say, in that aquifer, in that particular case, in that particular experiment, it was 17 centimeters at least.
Excellent. Obviously, the interest on Grace is that we have challenges in terms of data scarcity, and if it can fill the gap and help us to be able to say something about what's happening in the aquifer, this is obviously something that is welcome. So thank you so much, Zaid, for those responses. Colleagues, we are looking at the time. It is 12 hours Central African time. And I think we should be winding up with a discussion. And as chair, I just wanted to highlight some key aspects that have come out from the presentations of the speakers. Nadia did a very nice job, although it was in Portuguese, but at least we were able to pick from our interpreters that the dry bed aquifers in the Limpopo system seem to be of favorable water quality for irrigation. And obviously from a climate perspective, we're very interested in both good quality water to meet the demand, as well as also the quantity that is required to make sure that we're able to irrigate and survive under stress conditions that climate might pose. And then we also had a nice presentation from the team from UWC, who were talking of this idea of using derivative analysis. And what I did is that we need to characterize our aquifer system in a way that it helps us to facilitate these important modeling frameworks, and also to be able to perhaps make those very important decisions when it comes to the modeling frameworks and implementing different tasks that are to do with characterization of our aquifer systems. I think derivative analysis is something that we want to see more and more being used, and hopefully we can get some update in terms of additional outputs that would have come out from that work. Then Lindani did show this very nice formulae, so to speak, that looked at water quality reporting to do with SDGs, and it's important that we do capture this because obviously it gives us a way of measuring how far or how far we are ahead or how far we are behind towards meeting our SDG. And some of the statistics at the moment do show that, for instance, SDG 6 is way behind. I think we are less than 50% in terms of, meeting those aspects or targets that were set out for that aspect. Then Marina, I think, did make a presentation that highlights this very nice, hotspot mapping. And I mean, we all know that since Southern Africa is very dependent of groundwater resources, it's important that we know where these hotspot areas are, so that our, to facilitate this aspect of IWM, we need to have that, information so that we know how to optimize our resources to meet both the needs of the environment as well as our human needs in that regard. So I think those outputs that point towards consolidating population, risk and aspects to do with surface water risks, and of course the groundwater, drought risk are things that our stakeholders, our decision makers, want to highlight. Chedza and Zaid are proposing this reviving of the groundwater drought risk map, and I think Grace is something that we all as scientists, stakeholders are looking out to fill that gap in terms of how we can perhaps address these data scarcity issues in the region, but also make it more user friendly. And demystify this aspect of, obviously it's got too much errors, it's too cost. Maybe we can find a way of utilizing these aspects. A very comment I also have from Dr. Andrew Bullock, who says the critical issue in assessment of pathways out of poverty to him is through farming, and gives an example of some assessment which was done, I believe, on Africa infrastructure diagnosis. And this somehow showed, or at least was very critical in distinguishing between pathways of food availability and pathways out of poverty. And to him, this is a very critical aspect that we should look at when it comes to groundwater for food security. And any progress towards these important connections between pathways out of poverty would be something that in a more general way would be important towards also linking this aspect of physical aquifer characterization or physical aquifer behavior to link it to livelihoods. We are still lacking on this aspect of these linkages. I can see that Micah is already online now. But before I leave, I wanted to request us colleagues that we put on our cameras so that the communication team can capture at least a group photo for reporting purposes. Please help us with your cameras, and then I'll hand over to Micah. So Micah, over to you, and then as we take that group photo. Thank you so much, colleagues.
Wow, thank you so much, Dr. Kawawa Banta, for steering the ship, in the last session. You have done very, very well. The only thing is I can only clap myself, the others won't be able to clap for you. You have done very well, my brother. Thank you so much. You have steered the ship to the extent that we are now back on track. So I would like to thank you so much. I'm an accountant by profession, but I hate derivatives analysis now in groundwater. That's quite surprising for me. We only thought that those are found in financial management, but now in groundwater, it's super. So thank you so much, Kawawa, for the good work that you have done. Now, colleagues, we are at 12:07. It's our comfort break. Now we need to go for a comfort break and come back and go into the last session just before we go into lunch. So can we meet at 12:15? This is going to be 12:15, 12:15, so that we can continue with the program. Thank you so much, participants, attendees, for asking so many questions. Keep them coming, keep them going into the chat box, they will be responded to. Thank you so much, colleagues. Let's just go for a comfort break and meet at 12:10. So without wasting much time, I would like again to call upon my colleague, Kasonde Mulenga, to come and chair this next session. And just to remind you that, we're still dealing with our theme, for the day, that the climate change challenge for urban water and food security, the threats and the role of groundwater. So this next session is also going to address some issues, aspects about the issues to do with climate change. So Kasonde, are you ready?
Yes, I am. Thank you so much,
Over
Mike.
to you, my brother.
Thank you.
Over to you. Can you chair for the next session? And James Manda, just to announce, is also our rapporteur for this session. Thank you.
Thank you so much. Yeah, the first presentation that we're having in this session will be done by Abongile. He's ready, I can see. The title of the presentation is Application of Integrated Geochemical Approach to Evaluate Hydrochemical Processes Influencing Groundwater Quality in the Western Cape province of South Africa. Over to you, Abongile.
Thank you very much, Chair. I'm still trying to put it on presentation mode. Is it showing?
Yes, it is showing.
Okay, thank you, Chair. Good day, everyone. My name is Abongile Klaza, and I'm from the University of the Western Cape, and I will be presenting under the topic, Evaluating Hydrogeochemical Processes Influencing Groundwater Quality in the Henningness Catchment of South Africa. So this is the key literature informing the current study. The study of hydrogeochemical processes has been an area of interest in the past few decades. Chemical variation of groundwater can reveal the interaction between groundwater and the environment, and thus provide a scientific basis for water resource management. Groundwater chemistry of a region is generally not homogeneous. It is controlled by geochemical processes, flow and recharge processes, and possible presence of contamination sources. Hydrogeochemical processes of groundwater help to obtain an insight into the contributions of rock or soil water interactions and their anthropogenic influences on their groundwater quality. This is the research framework of the study. So the current problem that we're facing is that with the increasing effects of climate change on the surface water resources and the increasing demand for water use, using groundwater remains an alternative water source. However, the reported poor quality of groundwater remains a challenge. So the question that we ask now is, what is the role of hydrogeochemical processes on groundwater quality? We argue that with the limited application of an integrated geochemical approach to explore key hydrogeochemical processes, this leads to a limited knowledge in the influence of the observed groundwater quality in the aquifer systems. Nevertheless, an improved understanding on what influences groundwater quality can lead to innovations that can be used to either purify such waters for the benefit of the water users. So the objective of the study was to assess water chemistry and relate the current groundwater quality. And also to establish the dominant hydrogeochemical processes that influence groundwater quality in the study area. So this is the current study area. The Henningness catchment covers an area of 1,400 square kilometers and is located in the southernmost part of South Africa in the Cape Agulhas municipality. As you can see in figure 1, the catchment covers 5 quaternary catchments, which is J50B, C, D, and E, and F. In figure 2, it shows where the locations in the catchment where the samples were actually collected. So these are the methods and materials that were followed. Groundwater samples were collected in pre-cleaned 1-liter polyethylene bottles after pumping out water for about 10 minutes to remove the stagnant water from the well. Temperature, pH, and electrical conductivity were measured in the field at the time of sampling using a Hach HQ40D multimeter. The samples were then analyzed at the National Department of Agriculture laboratory in Elsenburg using an inductively coupled plasma optical emission spectrometry, also known as the ICP-OES. These are the results for the current study. As you can see on both the wet and dry season, the dominant water type in the study area in both seasons was sodium chloride type water. This is typical of coastal aquifers. This water type signifies as water that is ancient and of oceanic origin. If you look closely at both the wet and the dry season diagram, the paper diagram show that 2 samples, which is piezometer 19 and bowl 10, plotted separately from the rest of the cluster of the samples for both seasons. Piezometer 19 plotted near the mixed water region, which implies that sodium and chloride were not as dominant Instead, ions were present in almost equal proportions, whereas for borehole 10, the dominance of calcium and magnesium was slightly more pronounced as compared to the rest of the samples. This is typical of groundwater in mountainous regions. To assess the functional sources of dissolved chemical constituents, Gibbs diagrams were employed. These diagrams assess the functional source of dissolved ions as precipitation dominance, rock dominance, and evaporation dominance, which control the water chemistry. The distribution of the sample points in the Gibbs diagram, which is figure 4, shows that the ratio of cations and anions of the samples fall in the rock dominance for the wet and the dry season zone, suggesting that precipitation induced chemical weathering along with dissolution of rock-forming minerals. This suggests that chemical weathering of rock-forming minerals is the main causative factor in the evolution of the chemical composition of groundwater in the study area, followed by the evaporative dominance in the wet season and the precipitation dominance in the dry season. We then move to bivariate plots. The first figure here, which is this one, the sodium chloride relationship has often been used to identify the mechanisms for acquiring salinity and saline intrusions in semi-arid regions. If sodium comes from only halide dissolution, the sodium chloride ratio is approximately 1. As you can see in the R squared here, the ratio is actually 0.98, which is fairly close to 1. Figure 5 shows which is still on this figure, shows the relationship between sodium and chloride in the study area. The sodium and chloride ratio of some of the groundwater samples are greater than 1, indicating that sodium is not only derived from halide dissolution, but also from other processes such as silicate weathering, cation exchange, adsorption, or anthropogenic activities. We thus moved to determine if weathering processes were one of the dominant processes influencing the groundwater quality in the study area. We found out that weathering processes account for 65% of the variation in the groundwater quality. We thus ruled weathering processes as one of the dominant processes in the study area. We then moved to determine if anthropogenic effects were influencing the groundwater quality, and we found that that anthropogenic effects only influence about 34% of the variation in the groundwater quality in the study area. So this is according to statistical significance, this is not really significant. So we ruled out anthropogenic effects as one of the dominant processes in the current study area. Okay, so to conclude, to define groundwater chemistry patterns and to provide reliable information about the processes that control the groundwater mineralization within the Henningness catchment, an integrated geochemical method was used. The geochemical assessment shows the dominance of sodium chloride water type resulting from the cation exchange process and the dissolution of halide dissolution. The first process of mineralization is reverse ion exchange reactions that caused the depletion of calcium ions and magnesium ions content and the enrichment in the sodium ions. The second process is the dissolution of halide attested by the sodium chloride ratio close to 1. Thank you.
Thank you so much, Abongile. Much appreciated for your presentation. We'll then move on to the next presentation. I'll just like to encourage participants to take note of questions, just jot them down and keep them. We'll get back to the question and answer session later on after all the presentations have been done. So the next presentation is from Sivashni Naika. And the title of the presentation is simply Mutapaland, the perfect storm. Over to you, Sivashni.
Okay, sorry about the slight delay. I thought I was third on the list there. Thank you. So I just want to check if everybody can hear me.
Yes, we can hear you.
Yes, you can.
Okay, thank you. So the presentation is on. Just go to. Okay, so it's Maputo Land, the perfect storm. So why the perfect storm? It's essentially a combination of factors, and I will go through each one during the presentation. I do want to acknowledge my co-author, that's Sue van Rensburg, and she's from the South African Environmental Observation Network. So just on the location of Maputo Land, and Maputo Land is basically the entire W70A catchment. So this is located in the northeastern part of KwaZulu-Natal. It's sort of the South African border side between South Africa and Mozambique.
Sivashni, did you have your presentation? Because we can't see it now. If you can please.
Can't.
Yeah.
Okay.
Sorry to barge in like that. Because we were able to see it just as you started. Okay, yeah, it's coming up. Yeah, there. Just take it to full mode, full presentation mode. Yeah.
Is it fine now?
Thank you. You can proceed.
Okay. So Maputo Land basically falls within a transboundary aquifer, and we're looking at this coastal sedimentary basin 6, which is here again on the northeastern side of South Africa, sharing between Mozambique and South Africa. It forms a little, it's about 5% of the Lesotho Maputo if you go look at transboundary basin boundaries, and it forms majority of the part of the Mbuluzi catchment in the Mozambican side. So just a bit of background on the study area, and I will focus mainly on Lake Sibaya. So Lake Sibaya is the largest freshwater lake in South Africa. It's linked to the primary aquifer system. So this coastal sedimentary aquifer, that's the W70A catchment, it's linked to this aquifer, and it's groundwater fed into the lake. So it's part of the Greater St. Lucia Wetland Park and was declared under the Ramsar Convention as a wetland of international importance on the 28th of June, 1991. So you'll see in the bottom, the large Lake St. Lucia system. It will go northwards to the Ismangiliso wetland area towards the lake. A lot of these polygons that I've highlighted with various colors, those are the water supply schemes. So you will see that this green one and these two green ones, they supplied majority from the lake itself. Now, just a few numbers to throw on the capacity of the lake. It's around 400 million cumegs. So this is larger than the largest dam in the Western Cape. And in comparison, here on your left-hand side of the catchment is the Pongola Port Dam. Now, the Pongola Port Dam is, it's the 5th largest dam in South Africa, and it has a capacity about 2,500 million cumegs. Now, what's interesting, and just to note, is that the catchment divide is the Limbombo mountain range. And that's around here, just sort of on the outlet of the dam side. But the floodplain for the dam is this Pongola River that crosses the border to Mozambique. So this floodplain is located around the Pongola River. It fills in, it has numerous wetlands and pans throughout the way. Now, focusing on the lake system, the lake itself is divided into 5 zones. So you have the northern arm, the western arm, which has the seasonal rivers of the Msileni River, the southwestern basin, the southern basin, and the main basin. So the deepest part of the lake is around 21 meters above mean sea level. That's located within the main basin. And the southern basin, the monitoring station, the Department of Water and Sanitation monitoring station, is located in the southern basin. Okay, so coming to one of the factors that are the input to the perfect storm, we're looking at forestry. So stream flow reduction activities that are taking place on the northern part of the lake and the southern part of the lake. So the northern part is the Mazangwenya plantation, and you can see I've highlighted it, you can see it here in this green outline on the northern side of the lake. And the other plantation, the Mbazwana plantation, is here in the southern side. Now I wanted to show you a time lapse. So one of the earliest Google images or Google Earth images that we have of Lake Sibaya is 1984, but I thought, okay, 5-year intervals. Let's start with 1985. Now you'll see with looking at 1985, you'll see sort of an outline on the western side of the northern plantation, but they haven't really developed the forestry in that part. And in the southern part, you also see a bit, they're starting to develop on the western side of the Mbazwana plantation. So these two plantations, it's more mostly a combination of pine and eucalyptus. And pine and eucalyptus, as we all know, are quite deep-rooted vegetation, and they draw a lot of the groundwater. So you find that their root system is predominantly around the water table, in the water table. Now moving on to the next image, you'll see in 1990 that the northern plantation, you'll see more greenery on the western side, and the southern plantation looks more or less the same. Now the lake levels and the volumes of the lake, it looks about similar. So it looks almost at capacity within these two images. So moving on to 1995, in the northern side, there's more development on the western part of the plantation. And you will see, if you note the lake, you'll see a bit of a circumference around the lake. So a bit drier area starting to show. Then in 2000, you will see that the southern plantation, the Mbazwana plantation, it's more greener on the western part. And in 2005, a lot more plantations happening, and you can see that the lake levels are decreasing. You will see a lot more drier or barren parts around the circumference of the lake. Then again, in 2010, you'll see more or less the similar sort of image. But the thing I want you to note is with the zonation of the lake, the southern part, and then the main basin. So the main basin feeds the southern portion of the lake. Now in 2015, this is where things get interesting. You will see that the lake area has been disconnected. The main basin and the southern basin has been disconnected. There is some sort of dune system that separates the two. So now there is no inflow from the main basin to the southern part of the lake. this continues, and this 2018 image is the latest one that we have, where you will see it's very dry around the lake. Even the plantations are not looking as green as they used to. So what's been happening? Now, the DWS station that I mentioned that monitors the lake levels, unfortunately, it's in the southern part. And because the lake levels declined, we stopped monitoring around the time of the disconnection, so around 2015, 2017. Now you'll see with this graph that I've shown, the lake levels are in the southern part is this blue line. And the graph goes about 2015, so it's just above 16 meters at that point. Precipitation is, the average precipitation in the area is around 500 millimeters. So you will see that even with around about the normal precipitation, the lake levels are still declining. So the DWS, we do have a few monitoring boreholes that is within W70A. So I've just highlighted a few that's surrounding the lake. So what's happening in terms of the groundwater levels. So you'll see with this W7N 0015, this is on the northern side of the lake. And the groundwater levels have started to decline by around 2014. Then the other borehole that we have is closer to the seasonal Msileni River, and it's been declining from the early 2000s. Then the other borehole that we have, it's also been declining around 2004. Then the W7N 0017 boreholes also shows a similar pattern to the one on the northern side of the lake. It's been declining from 2014. And the borehole on the southern side of the lake has been declining from about 2003, 2004. So they have very similar patterns. And the last one that I will show you is located in the Mbazwana plantation, and that's also been declining from 2014. So you will note that what's interesting is with the groundwater levels, they've been in decline. And like I was saying previously, it's a combination of factors. So forestry, we did look at. The other aspect that we need to further look at is the effect of the lack of flood releases from Pongolapur Dam. So the Pongolapur Dam, and only recently they've been fitted with operating rules or yield curves for the dam. Now the dam has supposed to have an annual flood release that goes to Mozambique, and that has stopped since 2014. Is it a coincidence? Unfortunately, we don't have monitoring boreholes within the flood plain to actually try and correlate, but I think that some work can be done, and we're looking at some work being done through the GRACE data. Now the water balance for Lake Sibaya, the eucalyptus on the Maputaland coastal plain is planted in high density at around 1,666 trees per hectare. This is managed by the TMM forestry. So it's the Temba and Bilo Mabaso councils that manage the forestry, whilst pine is planted at 1,111 trees per hectare. So a daily average consumption of 2.35 megamillion cumegs a day equates to 858 million cumegs an annum, which is about 1.5 orders of magnitude greater than the projected human consumptive use from groundwater. So if we look at the inflow component, majority of inflow to the lake is from the groundwater. So it's around 40%. Then the second is rainfall, and then the third is runoff. Now the outflow from the lake, majority is evapotranspiration. Then we look at abstraction from groundwater in the surrounding groundwater fed area of the lake, direct abstraction from the lake, which the municipality is still doing, and then the groundwater outflow. So to maintain that equilibrium between freshwater and saline water, a certain portion of groundwater has to leave the lake area towards the ocean. So what has the department done in terms of trying to protect the lake? Around 2017, we published resource quality objectives. So resource quality objectives is it's a classification system where we use to manage, it's not part of licensing, it's just a way to manage that catchment. It's a way to try and protect the ecosystem side and then try to sustain the water supply side. So the Lake Sivai catchment is a groundwater-driven freshwater lake catchment. The part of the catchment outside of the nature reserve is extensively covered by commercial plantation, where a considerable amount of groundwater is pumped. This plantation use has impacted both the groundwater and the lake, as indicated by lake and groundwater decline. Further plantations within the catchment should be discouraged. The groundwater ecological reserve is very high. Approximately 60% of the recharge, therefore all groundwater lake activities within the groundwater contributing area of the lake needs to be monitored. The median lake level over a 30-year period should be around 17.39 meters. So the current lake levels in terms of the main basin, we're looking at around the 14 meter mark, And then the southern basin is very, very low. So it's around the 4 or 5 meter mark. If we don't have enough mitigation towards this lake system, we will lose the southern basin. So in conclusion, with this perfect storm, we're looking at the effects of climate change in the area. Maybe it's the lack of tropical cyclones affecting groundwater recharge. So a lot of climate models in the area predict either way. It's either an increase of high intensity recharge or rainfall events. And then the other ones are more looking at a shift of tropical cyclones. Instead of touching down in W70A, they're shifting towards the Mozambican side, so the Maputo side. Then we have to look at the socioeconomic impact. Afforestation is developing uncontrolled in the area. Use water-wise economic activities are needed in the catchment to sustain the population in the long term, but ecosystem integrity is equally critical. Lack of alternatives for domestic water supply. Because of the low levels in Pongolapur Dam, there has been increased groundwater development. There are no other surface water options. And the lack of flood releases from Pongolapur Dam. So the last was 2014. Has this had an effect on the groundwater recharge? So thank you very much. And I'd just like to acknowledge again Sue from Scion and Mark Scarpers from JJ Africa, Yanni Bates from Umvoto, and then my colleagues from DWS. And this is just a few pictures from the Southern Basin. Thank you.
Thank you so much, James, for that notification. Thank you for the presentation, Sebastian Naika. I understand why the title is The Perfect Storm. I was wondering before you did the presentation. We'll then move on to the next presentation that will be done by Thandizwe Bengeza.
Yes.
The title of the presentation is The Use of Basement Water in Urban Areas. So I'll hand over to you.
Okay.
Thandilizwe, go ahead, please.
Thank you. Hi, everyone. My name is Thandilizwe Bengeza from Department of Water and Sanitation in South Africa. My presentation is about the use of basement water in urban areas. The background for the case study. As we know, South Africa is a water scarcity country, and urban areas have higher water demand due to population growth and increased urbanization. There is an urgent need to investigate alternative water sources because urban areas use surface water and now is fully allocated. That's why there is a need to look for alternatives. Basement water is identified as one of the potential water source in urban areas that can reduce the water stress on municipality water supply systems. The main aim of the case study is to promote the beneficial use of basement water in urban areas. This is the map of South Africa showing the case study. The case study is within Gauteng province in the city of Tshwane, CBD. This map is showing the location of the buildings that we investigated in Pretoria, CBD. The method that we used to investigate, we did hydron sensors where we identified the buildings with potential basement water in their buildings. And we used 3 methods to determine the water quantity, which is level logger and hour meter and bucket method where it's suitable. The level logger was used to determine the flow rate and also the sub yield. The hour meter was used to measure the time corresponding to the sub yield and the energy that is required to pump out the basement water. And also the bucket method was used to determine the flow rate. Water sampling was done for water quality purposes. And business cases was also conducted for cost benefit analysis and also the upscaling of the benefits of basement water use for across the city of Tshwane. The outcomes for state theater. The potential sub yield for state theater is 133 kiloliters per day. And the water demand is 136 kiloliters per day. The sub yield can cover almost 98% of their water demand. And the water quality results comply with sense standards, drinking, and also the irrigation guidelines. Only exceptions in this case is turbidity. We propose the potential use of basement water for this state theater, air conditioned cooling system, fountains, and flushing toilets. We did a business case for state theater, cost benefit analysis. The cost of the water use at state theater is around plus or minus 900,000 per year. And the basement water is equal to 98% of their water demand. This is very important part. Between 60% to 75% of their water use is for air conditioned cooling system. That's why we did the cost benefit analysis for air conditioned cooling system. that if they decide to use this basement water for air conditioned cooling system, the cost is around 1.5 million. And the maintenance and the operation, it's around plus or minus 144,000 per year. And all of these costs, the capital cost can be recovered in 3-year period. So this proposal is economically feasible and efficient because they will save water and also they will save money after 3 years. The results for Reserve Bank, the potential sub-yield for Reserve Bank is 155 kiloliters per day. And their water demand is 112 kiloliters per day. The sub-yield can cover the entire water demand and have surplus of 43 kiloliters per day. And the water quality comply with SAN standards. And in this case, we don't have any exceptions. And the potential use of basement water for this building can be used for fountains, car wash, air conditioning cooling system, flushing toilets, etc. The business case for the Reserve Bank, cost benefit analysis. The cost of the water use in the building, it's around plus or minus 700,000 per year. And the total cost of basement water use, it's around 1.8 million. Maintenance and operation and the energy and the chemicals that can be used is around 200,000 per year. And the total cost is plus or minus 2 million. And also the capital can be recovered in 3-year period. So the proposed option is economical viable and feasible option for a Reserve Bank to implement it, because they will save a lot of water and also money in their case. But in this case, they can use the basement water for the entire water demand. We also did our investigation on Swane House. The potential sub-yield is around 52 kiloliters per day, and the water demand is 45 kiloliters per day. And the sub-yield can cover the entire water demand and have surplus of 7 kiloliters per day. And the water quality results complies with SAN standards. Only exception is turbidity and bacteria. And the options is air conditioned cooling system and fountains and garden irrigation. Cost benefit analysis. They are spending around plus or minus 400,000 per year on their water use. And the total cost of basement water use, it's around plus or minus 500,000. And the maintenance and operation is around 150,000 per year, plus or minus. And all of the capital cost can be recovered in a 2-year period. And we propose that they can use this basement water so that they can save a lot of water, decrease the water stress on our municipality water supply system. And they will recover their money after 2 years. And upscaling benefits of basement water for the city. The average range between 1.1 to 2.3 million liters per day of the potential basement water that can be beneficially used in the Tshwane CBD. These potential yields are highly ascertained, but this shows that the total potential water supply available for the city of Tshwane for basement water for beneficial use can be used. It's very difficult to give a correct or accurate number because of we didn't do any audition, because the buildings, they are just abstracting this water and discharge it to storm water without measuring it. So it's very difficult in terms of upscaling. But this at least give us the indication of the water supplies in the city of Tshwane. Our conclusions is that we in city of Tshwane, we have enough water and good water quality, more especially if we are using this basement water for secondary use. They won't need a purification processes if they are using for irrigation, for instance, or also for flushing toilets. And this do make economical sense to develop the basement water, because they will save money for buying water from the municipality. And also we propose, if they don't want to use the basement water for entire building, we propose some of the alternative use like garden irrigation, flushing toilets, etc. And our recommendation is that we developed a generic approach to basement water use and also an implementation plan. Generic approach will help us to decide if the basement water will be feasible for use, and also it's worth it to invest on it. While the implementation plan should address should address the basement, how the basement water should be encouraged and also as implemented in this case. Thank you.
Thank you so much for that presentation, Thandisirwe. We'll then move on to the Q&A, covering all the presentations in this section. Let me move on to one question that has been asked, directed at you, Thandisirwe, from Brighton. The question goes, what informed the selection of the investigation sites? Was it the hydrogeology or demand or any other factors? You mentioned in your presentation, there was the State Theatre, there was the Reserve Bank, and then there was the Tshwane House. So what were some of the considerations for choosing these sites?
We investigated around 20 buildings. We only chose 5 buildings because it was easy to have access, and also they were pumping a lot of water into the stormwater. That's why we chose these specific buildings.
Okay, thank you for that. I just wanted to find out, in your presentation, when you were concluding, you mentioned you've developed an implementation plan. So
yes,
has this been shared with the relevant authorities? Because you know the figures are quite staggering. If you look at the Reserve Bank, they've got a potential yield of 155, and then of course the demand is 112. So if there was utilization, there was obviously be a lot of saving of money if it's followed through. So has there been any buy-in from the
Yes. Reserve Bank, 3 of them, they promised that they will develop this basement water because we were working with them. They are aware of, they have a lot of water that they can be used in their buildings. And in that implementation plan, it is divided in teams. For instance, the first team is awareness. That's what I'm doing now, because in that implementation plan, it said we must share in conference and go and present. And I think the second theme is about the buildings, the operations, that we have to talk to the buildings and inform them about this so that they can take it forward. And also engage municipality in terms of strategic planning and our Department of Water and Sanitation so that they can include in their integrated development plans. I hope I answered your question.
Yeah, thank you for that. I think it will be important as well, just a presentation to the council, not the like the State Theatre or the Reserve Bank, but the building council, so that in the planning phase, this is taken care of, so that it's mitigated. We don't move from a situation where you have a building already and then you come up with the solutions. But if that is tackled in the planning phase, you look at where the building is situated, the potential yield, and the stormwater that's going to be generated, and then begin to use that as part of the value chain.
Yeah.
Thank you so much for that, Tandiziro. I've got a question for Sivashni on your presentation. I just wanted to find out as well your recommendations, whether they've been presented to the council in the area. Have they, taking on your recommendations and your conclusions for the study, because it is a perfect storm there, if you look at your findings.
Yeah, it's difficult because I think with this one, it's such a collaboration and such a mix of issues. I mean, the forestry has been the community livelihoods for a very long time. So we're looking at the previous Water Act, which was 1956. So they have, in terms of licensing, they had an existing lawful use license. So with our new National Water Act, we can't really tell them, okay, they have to do things differently. So we're trying to engage with them more on a personal level to say, or to see what other activities they can explore, such as tourism, other options for them. Because it's been a problem because they don't really irrigate the forestry part, since the plantations are quite deep-rooted. They are abstracting groundwater. Then another issue is that they seem to be moving into wetter areas, so like wetland areas with the forestry and things like that. So it's a lot of things that, and a lot of people that we have to engage with, even on the supply side, who they're supplying commercially, to say, you know what, this is not sustainable. How can we have different options presented to them at the table? So it becomes, a very complicated issue,
Thank you for that. Going back to Tandiziro, there's just a comment there from someone. There are some studies that looked at the development of basement fractured aquifers, e.g. in the Limpopo bulk water supply. The comment is that you might want to consult them in refining your methodologies. Any comment to that?
Can you repeat the question?
there was a comment that said there were some studies that looked at the development of basement / fractured aquifers. For example, in the Limpopo bulk water supply, you might want to consult them in refining methodologies in how you go about, with refining your methodologies as you further your studies on this.
Yes, I would love to.
Okay. I'm looking at the Q&A section, trying to see if there are any other questions that have been generated from the presentations. STK, go ahead.
There is a question here. I don't know whether it has been addressed or not. It came, I think, from Brighton. It's around about 112. It says, can groundwater be successfully implemented as a bulk water resource within rural Limpopo province? Analysis based on GRIP data sets. So I'm not sure who was he addressing the question to, but that's a question of which I'm not too sure whether it has been addressed or not.
No, TK, it's not a question. Sorry, Chair. It's one of the sources that maybe, is it Tandezile, the one who did the investigation on basement aquifers in the Limpopo? Might want to consult if they've not done so. Thank you.
Okay.
Thank you. I see there's a question from Dr. Andrew Bullock on the development on developing basement groundwater. How important is tapping into fractures? How do you get to identify these? Tandilizwe?
Okay, let me first define what do I mean by basement water, because we are not talking about the aquifers that we are typing to the aquifers. The basement water is the water that is entering the basement or underground parking and is being removed by the watering system to ensure the dry conditions. So in this case, let me first answer that one about Limpopo. In Limpopo, they don't have these buildings that they are pumping out this water. We are talking about the urban areas that they have the underground structures. And to manage groundwater levels, they are pumping out into stormwater. So this case that is about taking that water use for beneficial use rather than just throwing it away. Not specific about you're not talking about basement aquifers. No, basement water. I hope I'm...
Yeah, so this is water that basically comes in through the stormwater drains as a result of the way the buildings are, say, erected.
Yes.
With reference to the surrounding infrastructure.
Yes.
Okay.
Yes. They are just managing the groundwater levels by pumping out that water into stormwater to ensure that the environment is dry. So we are saying, how can we use this water that we are just pumping out and throw it away into stormwater? Not per se as a groundwater, as a basement aquifers, no.
Thank you for that. Thank you. Okay, if there are no more questions, maybe we can move towards wrapping up of these particular sessions. We've had 3 presentations. presentations quite interesting. The first one was the application of integrated geochemical approach to evaluate hydrogeochemical processes influencing groundwater quality in the Western Cape. And then we had the Mutapaland, the perfect storm, presented by Sivashni. And then lastly, we had the use of basement water in urban areas by Tandilizwe. So I'll then hand over to the chair, Micah.
Wow, thank you so much, Kasonde. It's greatly appreciated. You know, you have been able to make it within the prescribed time. We are supposed to go for lunch at 13:30, and then we come back at 1400. So, colleagues, you know, there you are. That is the last session, you know, for the morning. I would like us to remind, you know, you colleagues that if you can complete the conference register, as well as the special session attendance register, which is going to come out in the for the afternoon section. Both registers are in the chat box. So if you can get hold of the chat box, please, can you at least be able to, can you, you know, work on those two registers and make sure that your name is registered. So thank you so much, colleagues. It's greatly appreciated. In the afternoon, we are going to come back. I think we covered the theme of the day very well since morning. And in the afternoon, we are going to have a special session, which is named Groundwater for Food in Africa, the current opportunities and challenges. This session is going to be chaired by Dr. Kevin Peterson, and our rapporteur for the afternoon will be Sivashni. I think she was presenting earlier on. She will be our rapporteur for this afternoon's session. So the afternoon session is going to be very, very interesting, and I encourage all of us, you know, to join in. It's all about, you know, knowledge sharing, and it's going to be quite intensive in terms of discussions around the subject matter. So, colleagues, we are still about 10 minutes to the prescribed lunchtime, but I suggest that we can now break for lunch, and we should be back, you know, for the afternoon session at 1400 hours, 2 o'clock in the afternoon, promptly, so that we can be able to deal with the afternoon session, which is very, very interesting, as it's a special session. So with those few words, colleagues, I would like us to break for lunch now, and let us meet promptly at 2 o'clock. And in the meantime, the technical team can you please play some videos to keep some who are seated on their computers entertained until after lunch. So thank you so much, colleagues. I'm very happy to be coming back after lunch, and then we'll continue with our program. And thank you so much for today. Thank you so much to the presenters who have you know, made a very good job today of delivering their presentations on time, and also very, very interesting presentations. It has been a busy day today. So thank you, colleagues. I will meet you later at 1400. Bye for now. Welcome back, colleagues. I hope you enjoyed the lunch break, and you are ready to go, you know, for this afternoon's session. I would like to welcome you. I know our numbers have gone down a little bit, but we expect, you know, a number of our attendees and participants to join us as we go along. So I would like us to get going for this afternoon session. You know, in our internal meetings at SADC-GMI, the Executive Director, James Aramba, is always asking about, asking this question, you know, groundwater for what? And today, you know, in this afternoon session, we are going to get that answer, you know, from a groundwater for food in Africa, and also to look at the current opportunities and the challenges that come with that. So it's going to be a very, very interesting session, and it's going to be chaired by none other than my colleague, Kevin Peterson. He will chair this session, and as I said earlier on, Sivashni will be the rapporteur for this session. We've got some interesting papers that are going to be presented this afternoon. So stay tuned, and I would like to remind you again, you know, to register for the conference and also register for this special session. I think with those few words, I would like to call upon Kevin. I can see you are already in the cockpit and ready to go.
Thank you,
so
Micah.
I'll hand over to you, Kevin.
Thank you,
so
Micah.
much. You can take over.
Thank you, Micah, and thank you for the opportunity to chair the session. As Micah has rightly said, it is a very important session focusing on groundwater for food in Africa, current opportunities and challenges. We've got a number of wonderful speakers, presenters, and I think a very illuminating program. In terms of the process, we will run through the program. We'll allow the presenters to present their presentations, and once we've done, we've got an open session around 20 to 4 where we'll address all the questions that may arise. Can I please ask you, as the presenters present, to note your questions in the Q&A box, so while the presentations are ongoing, so that we, when the open session is there, we are able to immediately go into some questions. So without further ado, our first speaker is Karen Wall. Also, we all, or most of us, know Karen, and we look forward to your presentation. Karen, thank you very much.
Thank you very much, Kevin. Can you hear me?
I can hear you, Karen, and your slideshow is projecting.
Good, thank you so much. Thank you to the organizers, first of all, for putting on the conference and for having me as part of it. I'm very pleased to be among you, even though it's in a virtual sense. And also thank you to the session panelists that I have sort of helped organizing in terms of putting this special session together, which will discuss the issue of groundwater and food in Africa, current opportunities and challenges. So I'm very pleased to have the team around this, and I will do my best in terms of giving a introduction to kind of set the scene. At the same time, I will give some kind of kaleidoscopic overview of some of the work that IMI has been involved in and is involved in at the moment as well. So just to set the stage, I think it's safe to say that if we're looking at food security globally, then we're not really on track to reach the SDG 2 on zero hunger. And if we focus in on the African continent, this of course becomes more prevalent. And you can see sub-Saharan Africa is the one sort of at the top here of the graph to the left, with the number of people that are undernourished. in 2000, and 15 years later, the number has increased, and the coverage of nutrition people has decreased basically in the continent due to population growth primarily. So with this, I just want to, of course, make clear that we are up against a large challenge in terms of supporting food security, and in that regard, a lot of that has to somehow be developed through increased irrigation, and groundwater has a great role to play there. So that's where this is coming from. Of course, groundwater is also important for food water security and so on. So it has a role to play in many of the SDGs, but here we're focusing in particular on SDG 2. Here, you've probably seen this before, and we are in this special situation at the moment with COVID-19, which will probably result in a recession, or is already resulting in economic recession around the globe. And then maybe further down the line will be hit by an even larger driver, you can say, of change, which is climate change, and it's already there. So you can see there's a succession of events and drivers that we are facing at the moment. Water is in the whole picture. You can see talking about washing hands, but I think we all realize that it's not only about washing hands if we want to achieve the SDGs and address all of these challenges, and the food is a big share of that. So here you see another wave, which is, I like to call it the groundwater wave, and we can ask ourselves if the groundwater wave is going to hit us as well, hopefully in a positive way, in the sense that it can help us improve economic development, food and water security, and so on in Africa. Just an overview of how the water resources sort of feed into the food system here. You can see the major share goes into the production itself, and then it is of course also used for the processing and preparation and so on. I won't delve into that in more details. Maybe also just mentioning that it's not just a matter of food security, but also nutrition security. And that's sometimes a bit lost. We only look at calories, but we also need to look at how good the food is. Another thing to bear in mind as we go forward is, of course, that if we are doing irrigation, that's oftentimes the major share of where the water goes. You can just see this upside down pyramid here, where if you have a smallholder household, then most of the water will probably go into the irrigated agriculture, less for livestock, and then a little bit for domestic use. But I think, as Barbara will also talk about later in the session, households use water for multiple purposes, from multiple sources, and they're doing that even for multiple livelihoods. So all of these things have to come together. We cannot really separate the various uses and sources. Coming back to irrigation, you can see the map here of Africa and the South Asian continent, and the African continent doesn't really stick out in terms of irrigation from groundwater. This is indicating the intensity of groundwater irrigation in those two regions. And in Africa, it's about 1% of the cultivated land, whereas in Asia, it's up to 14%. This is data back from 2010. This is some data that I collated in 2013, just to see if there's any kind of trend from early 2000 up to 2010 in terms of groundwater irrigation, focusing on sub-Saharan Africa. And you can see there's been some increase. The numbers were quite uncertain, but at least we are seeing some increase, both in terms of area in million hectares, and also in terms of the share in percentage of irrigated land. To the left, you can see India and how the trajectory has been there from 1950, where it took off. And you can see that we're just at the very beginning and 50 years behind, basically, in sub-Saharan Africa. This is also work we did some years back, looking at the irrigation potential from groundwater using a water balance approach, looking at the maximum available recharge as the upper limit to groundwater abstraction for irrigation, but also accounting for other uses like livestock and domestic uses and environmental purposes. And then the rest was available for irrigation. In this particular map, we also compared it with what is already being irrigated from groundwater in Africa based on a map by FAO. And you can see whatever is left, whatever is green here is what is not committed already in terms of those groundwater irrigated areas. So that's basically where most of the sort of remnant potential for groundwater irrigation is today. And you can see, of course, the Northern Africa is already pretty much developed, and also large parts of South Africa. Just the variability between the countries, you can see again, South Africa sticks out quite well, but also that the numbers are quite small here. We're talking about thousands of hectares, very small numbers. And then, of course, we will ask ourselves, why does groundwater not take off in terms of groundwater irrigation, since there's a big need for the food production and food security, and the water resource is basically available to quite a large extent in many areas. And some people have been discussing this, whether it's sort of a precautionary approach to avoid any overdrafting issues that we have seen, like in South Asia and other places around the world. So donors are maybe reluctant to invest in these kind of new developments. I think there's probably some truth around that, and I think it's also fair enough to do that. We have to be precautionary, but I think at the end of the day, there are a lot of other constraints that come into the picture when we're talking about why it's not happening. And to explain other factors, I put this, what I call the groundwater value chain in agriculture together. And you can see groundwater is here. This is a resource that we've been discussing so far, which is basically there. But then we need the wells, we need the pumps, we need energy and power, and we need extension services, we need financial services for the smallholder farmers, and policies in place. And all of that is seldom coming together in one place to really drive it forward in a big way. One or many of these factors are oftentimes not there. So I think that's a big issue, and can explain some of the lag in development. What we found from some early work, and this is not only from my work, even though it only gives my name here. This is actually a summary paper from a lot of work that was done throughout Sub-Saharan Africa in terms of looking at what was happening on the ground for groundwater irrigation. And what we found was that groundwater is a preferred water source for many farmers, including women, when they expand from, for instance, rain-fed to irrigated agriculture. And oftentimes the farmers that use groundwater get a larger net revenue from their irrigation compared to other sources. Oftentimes they go for vegetable crops because that's a cash crop and they can make good incomes, and because the water resource is very stable and reliable, they're not losing the crops and they get a secure income. And we also see some of the adopters, like of various technologies, they also seem to gain, from those adoptions. In Ghana, for instance, we saw distress migration was reduced if dry season was cropped with groundwater irrigation. So there's definitely scope for more of this as we go forward. Some of the shortfalls is, of course, when you're dealing with smallholder farmers, because they have less financial capacity and other constraints, and especially the women, who are oftentimes the major farmers in Africa. They struggle to get the access to both land, to resources, to wells, to the economic means that they need to invest. So that's where we need to look closer at some of these equity issues. And I think we will be discussing this as we go forward as well. Just very quickly to give you a kind of a sense of what we're talking about. So here I tried to make a simple typology of groundwater irrigation in the continent. And I just did 2 axes. So depending on the depth of the well or the funding source. And I'll just show like a collage for each of these 4 types. So this is the deep wells that are sort of privately driven. This is an example from Ethiopia, where they grow intensive agriculture or horticulture with flowers that are being exported and sent to other countries. And this is quite intensive and commercial agriculture. Then still in Ethiopia, this is in Ghana, where you have also private investment in groundwater irrigation, but they're very shallow systems, smallholder farmers, very small plots. Some of the wells are even temporary. They're not drilled permanently, so they have to dig them every year. But they can still make a living and get a good income and secure their own food supplies as well. Now, if we go to the subsidized systems, this is back to Ethiopia here, where we have some public schemes that have been put in for smallholder farmers by using deep groundwater. And this is supporting very poor farmers to enhance their livelihoods through public means. Also through public means, or this is partly through World Bank support and others. This is an example from Nigeria, where they have the so-called FADAMA systems, small holder schemes and shallow systems, but in this case, subsidized by external sources. Okay, so going on to some of the work that IMI is now sort of engaged in to support some of these processes going forward. So we're looking into solar irrigation. We need to look at better drilling for irrigation and decreasing the costs so that the farmers can get access easily. We have to look at capturing some of the water in the ground to make sure that it's available for irrigation. And we can also use demand management, which I'll give an example of, where we use various soil moisture and nutrients management tools to decrease water and energy and nutrient use. And then at the end, we need to monitor much better and feed that back into management systems as we go forward. The demand side tools that I mentioned before, this is from our transboundary aquifer in Wamachwe, where we had 3 different sites. You can see here 2 on the Botswana side and 1 on the South African side, where we implemented these tools that can monitor the capture of water below the root zone and also the capture of nutrients. So you can see if you're losing a lot of this, and you can cut back accordingly. And this can be monitored on a regular basis, so farmers can have a pretty good real-time understanding of what's going on in their systems, and see that they're not also putting too little water, but actually still getting a good crop yield. Here you can see some data. I'm just showing one graph here as an example. This is for water productivity. You can see where there's no use of these tools. You have the blue, and where you have the tools, you have much higher productivity. So the water saving was found to be 40%, energy saving 30%, crop productivity was increased by 70%, and the nutrient losses was decreased by 60%. And this is accredited to my colleague Manuel. I think he might also be in the session today, and some colleagues. This is other work from the Limpopo Basin. You can see a smaller catchment here within the larger basin on the South African side, where we've been working since 2014 with the farmers in that particular catchment. You can see to the left, and now we're also expanding into the one to the right. But basically what we're facing here is quite shallow, not so productive aquifers that are prone to desiccation, either from climate change or from depletion. And you can see the historical record here, where over a 10-year period, groundwater levels have come down, and farmers have been struggling to get enough water for their farms. These are both smallholder farmers and big commercial farmers. And then you can also see in 2000 how the aquifer was very rapidly replenished due to the flooding, exceptional, like 100-year flood that happened during that time. So you can also see how the climate in this regard impacts very much the water resource availability. We looked further into this by numerical models across the catchment to understand sort of the storage changes over time and the various processes for replenishment. And we got a better understanding of some of these focused recharge and very episodical recharge events, which I think is becoming quite well known across the semi-arid areas, that this is when groundwater is basically being disproportionately replenished. At the moment, we are looking at citizen science in the same catchment, where we're installing rain gauges and groundwater monitoring together with the farmers, and capacitating them to do it themselves and to uploading it on a site online and feeding back the information to them so that they can use that information for management. So this is a quite nice new sort of a novel experience in South Africa. I think it's the first time that citizen science has been applied to groundwater. In the same catchment, you can see again here, we looked at Polokwane, which is the major city upstream in the catchment, and it's basically also running out of water. It's relying a lot on imports, but now it's also relying on reuse through wastewater, treated wastewater. And this is kind of a natural recharge system where the wastewater is being discharged into a stream and then infiltrated into the riverbed and into the aquifer, and then further downstream, as you can see in the diagram here, is being abstracted again for groundwater irrigation and also for water supply. So we're looking into the sustainability of this, both in terms of water quantity and quality, because there seems to be some potential water quality issues as well, particularly with arsenic. This is very critical to look further into. Then I'll go on to some of the last things here, which relate to solar irrigation. So IMI has been working on that for a number of years, where we are not only looking at the water resource again, but as we saw before, trying to integrate, across the value chain of irrigation, and how the farmers get access to this through different business models, and how it fits into their livelihood systems and so on. But in this context, I'm again focusing more on the resource aspect, and two parts that we are now looking at through two different projects. So one is to equip existing solar pumps with measurement instruments that can capture what's happening with the pumps through cloud-based systems. So when they're switched on and off, and how much they pump and so on. And then that information in the cloud can be taken down to be analyzed, and you can get information of when the farmers are pumping and how much and so on. So we hope that over time we can build systems that are smart enough to tell us, if there's any issue with the pumps, and also with overdraft of groundwater, and in collaboration with the farmers. This is still quite early phases, but we have sort of the technology in place, and we're piloting it now primarily in Kenya. Another aspect of solar irrigation is also it's covering the whole of sub-Saharan Africa, and we're basically looking at projecting into the future the demand and the opportunities for solar irrigation across the region, and also looking at what could the potential risks be if these potentials are being developed through solar irrigation. That's another project together with some of the solar irrigation partners that we're working with. So far, we have found some very preliminary results that the solar irrigation, or the solar systems, are primarily used for irrigation. They're again used very heavily for the cash crops that give farmers good incomes, like you can see on the photo here. And also we found that the market is rapidly expanding across the region. So my key messages to round off my presentation. I think it's safe to say that groundwater still holds a large potential for smallholder irrigation in sub-Saharan Africa. Groundwater is a preferred water source for many farmers because of its inherent properties, but we still need to curtail some of the other constraints for the farmers to get access. Also, very importantly, it provides this climate-smart livelihood and food approach, for the farmers. Groundwater has that particular property, which is very important. We still need to look at the sustainability and the equity as we go forward, and as this resource is developed, very, very important to come in also early on to look at that. And I think we are somewhat at the forefront of these things, much better than for instance, in India and Asia. So some of the new opportunities, I think I would like to highlight, I already mentioned them: solar irrigation, soil moisture and nutrient management tools, managed aquifer recharge. And I like to look at it in this recycling context, so that we look at peri-urban systems with using recycled wastewater, but in a sustainable way. That also keeps down the demand. Improved drilling methods. I didn't go so much into details of that, but that's also quite important. Citizen science and local participatory approaches, and then the sort of the climate smart, if you like, and groundwater smart monitoring that is needed. Also, like, for instance, looking at seasonal forecasting, so that we can know if the shallow groundwater systems are running out of water before it actually happens, and farmers can adjust accordingly. And then my last point here is to emphasize the importance of partnerships around groundwater for food security and more broadly in Africa. And I think these are expanding quite a bit at the moment, and we'll have some examples from that, especially from AMCOW in our session as we go forward. So I think I'll stop there. Thank you very much.
Thank you, Karen, for this excellent and very informative presentation. I'm not sure, is our next speaker, Ricardo from FAO, available?
It's Livia Peiser from FAO.
Yes, excellent. Can you share your presentation and move on?
Sure.
Thank you.
Sorry,
Thank
Dr.
you.
Peterson.
Yes.
Can I interject, please?
Yes.
Actually, there is a request from the interpreters that if our presenters can be a bit slow so that accommodate the interpretation process, please. They're just requesting for that.
Thank you. Thank you, Tokozani.
Thank you.
Okay. Could you please confirm you see my presentation?
I see your presentation and I hear you clearly.
Thank you. Okay, so thank you very much for inviting us, for inviting FAO to participate in this conference. I will present what we do in relation to addressing groundwater resources management through the lenses of the water, energy, food nexus, and also through the role of innovation and technologies. What I will be talking about in particular is how we define the nexus concept, what it is and what it contributes to this issue. Some examples of practical interpretation of this concept in our work in FAO, and some relevant tools for monitoring the nexus and groundwater use in particular. And here I will mention our database and technologies for monitoring water productivity through remote sensing. That's vapor. So let me, I hope I'm speaking slow enough, but I also hope this will not delay my presentation. So I'll try to find the balance. So the nexus concept, the way we see it, I mean, the history is that everything started in the Economic Forum in Davos, where for the first time, the global risk associated to water, energy, and food security were connected. This approach then evolved into the Bonn conference in 2011, where basically these risks were turned into opportunities and for addressing these challenges. So basically, the water, energy, food nexus describes the interrelated nature of our global resources system. And it's about understanding the different goals and interests and balancing them while maintaining the integrity of the ecosystem. So what's its added value? Basically, it's not something entirely new, but it's a frame for times of increasing competition, like the times we're living today. It has a convening power across and within sectors, and it recognizes the constraints and these interdependencies. And it's a flexible concept, and it provides a platform for building a common language. Initially, this concept, as we saw, emerged as a framework to facilitate a shift from sectoral and integrated planning, and also a vehicle to overcome policy fragmentation. So from the Economic Forum, then it went through the Bonn conference, then this concept became also prominent in the Agenda 2030. And FAO contribution to it is particularly is summarized in the publication on the nexus for food security and sustainable agriculture. I put there as a useful reference, I hope. But in practical terms, how do we see the nexus on the ground? Some examples are those related to solar-powered irrigation. This I will be mentioning this example in particular because it has direct implication for groundwater use. But other examples include bioenergy crops, for example. What are the trade-offs, particularly in situations of land scarcity? Do we allocate land for biofuel or for food production? And what are the water requirements for those? And this means that we need to increase and to look at the water productivity, the way water is used in these production systems. There's other practical examples of the nexus, such as hydropower, but maybe these are less related to less directly related, let's say, to groundwater. So I will primarily mention particularly the first one and the second one. So solar-powered irrigation is an amazing technology, and it's exploding. Well, exploding maybe is too much, but it's getting more and more common. And there's the problem that it has sometimes is that the price of energy used to have, so before, let's say, the solar power irrigation is in play, before that becomes operational, the price of energy used to be regulated, and it used to have regulating effect on the amount of water withdrawn. So when farmers need to pay for electricity or fuel, of course, that puts limits to the amount of water withdrawn. With solar power irrigation, this regulating effect is disappearing, and there comes a risk of overexploitation of groundwater. So clearly, with solar power irrigation, water accounting and irrigation monitoring becomes increasingly critical, not only to understand what is happening, but also because there are ways to cope with risk. For example, there are, in some, depending on the situations, these might include selling electricity back to the grid instead of using it for pumping, if that is a possibility. It's not always the case, or putting in place agreements in French Africa. You have this contrat de nappe. So there are agreements that or dialogues that make everybody aware of the safe caps of withdrawals. But to do that, again, you need proper water accounting and assessment of water consumption. FAO has engaged in this topic, and there are a couple of examples of resources that I would like to share with you. One is a book, a publication on the benefits of and risks of solar-powered irrigation, a global overview. And the other one is a toolbox that, well, to which FAO contributed, but it was done with many other partners. In these resources, these problems are addressed, and it becomes clear that there's two key options, not options, but more strategies to cope with the risk of overexploitation of groundwater in this situation. And these are a good, well, improving the governance and having tools to monitor water consumption and groundwater abstraction. And around these tools, these approaches, FAO has been working in collaboration with other partners. And I will mention particularly two projects that might be relevant in this conversation. The first one is happening in the framework of a project that is called Implementing the 2030 Agenda, and is focusing on North Africa and the Near East. And the other one example I will make is the vapor database and how it can be used to monitor groundwater use. So the first project I will refer to, or it's more program than a project, is this activity on implementing the 2030 agenda, and this focuses in particular through projects in Jordan and Morocco on nexus dialogues, and these nexus dialogues include a review of the individual sectors and discussion around challenges and solutions, development of integrated nexus models, and that feed against another round of dialogues that are supposed to then to take place on a longer term as well. Why they decided to focus on Jordan and Morocco, because both countries have unsustainable abstractions of groundwater, particularly for irrigation, of course, and because both countries are investing more in the energy sector, including in solar energy. Also, both countries are aware of the interlinkages between sectors and the negative impact that could derive by the lack of coherence in policy development. So the activity started by recognizing the trade-offs and the interlinkages between the water, the food, and the energy system in the countries, the conflicts and opportunities for integrated approaches. And I will, for the sake of time, I will summarize the lessons learned through this process, and I leave there also some, let's say, coordinates. If you're interested in that, feel free to reach out to that email address or to me, and I will direct to the relevant resources. So the lessons learned in this water, food, energy dialogue and activities are: the first one is, as said, that governance is central to Nexus implementation, that there are institutional structures and organizational cultures that sometimes induce inertia against the interministerial coordination. That's because of that also sharing data remains a difficult task, and also because there are vested interests sometimes, and there's often insufficient recognition of relevance of political and governance factors. So the dialogues hope to address some of these challenges by building a platform for overcoming some of these difficulties. So that's to go back to the type of approaches that we believe are important to address the nexus, and in particular in relation to to groundwater implication. So we mentioned some the governance aspect, and I will now quickly show what we do in terms of innovation to monitor the nexus, and in particular to monitor the impact on groundwater resources. Let me start by saying that we have this program that's called WEFE, that is a program that aims at monitoring water productivity in agriculture. And by water productivity in agriculture, we mean the amount of output in kilogram per hectare, so yields or biomass, per unit of water consumed in cubic meters per hectare. And these two variables are likely, are observable, or let's say, can be calculated and assessed through remote sensing, both the biomass and the water consumption through evapotranspiration monitoring. So with that, with this goal of the overall goal, of course, is to be able to produce more food with less water. We set up this program that's called WEFE, together with a number of international partners, including IHE Delft and the International Water Management Institute, with the support of the government of the Netherlands, and a public-private consortium that is behind most of the data production. So we take data from satellites and translate them into key water-related, water productivity-related variables like biomass, evapotranspiration, and so on, and also package this information in water productivity and water accounting estimates. The data is produced at the moment for the African continent, Africa and the Near East, and at different levels of resolution. So the whole continent is covered at 250-meter resolution. And while there are the darker areas, there are 21 countries covered at 100-meter resolution and 5 river basins as well. And 8 areas for which areas that correspond in most cases to irrigation schemes or watersheds where data is produced at 30-meter resolution. We publish the data on a portal, on an openly accessible open data portal, where every 10 days, starting from 2009 to date, these data are published. And so it's decadal data set on biomass development, water consumption, and also other agroclimatic parameters. This is an overview of the continental scale water productivity map. Basically, the green means that more than 1 kilogram of biomass is consumed per cubic meter of water. This is an example of the let's say middle level of resolution at 100 meters. This is a close-up of the Gezira scheme, and you can already see here that there's some spatial variation in the scheme. Sorry, I see that. Okay, 3 minutes left. Some spatial variations in the scheme, and that helps already targeting interventions on the field for closing water productivity gaps. When we go to the higher level of resolution, this is an example of the Bekaa Valley in Lebanon, we are able to identify the single fields and also crop types, and thus understands the water consumption of the different crops over time. And in this case, in the Bekaa, there's a combination of groundwater and surface water. So this becomes very relevant, of course, for groundwater management as well. We publish all the methodology and algorithms and make the data available through API for easier integration. I will just show quickly what type of information we can derive with that. So these are water consumption trends. The moving line shows the amount of cubic meter that go into water, into irrigation And this is an example of Fils de Niger in Mali, but this is not based on groundwater. So I'll just show quickly one example in the south of Egypt that is serviced by not only groundwater, but this is a fossil aquifer. So it becomes even more relevant to be able to measure how much water is drained to feed that scheme. And if we zoom in that area, we can see from 2009 to date how much this scheme is expanding, and we can calculate how many cubic meters of water were extracted to feed this system. So let me just conclude by saying that this information is made available, as I said, through API, so it can be integrated into application. This is an example of application they developed in Lebanon for providing irrigation advice to farmers. And we also do some quality assessment because we are aware that a lot needs to be done in terms of increasing trust in remote sensing products. So quality assessments have publications. And yes, I'll conclude by saying that we are growing in time and space, and hopefully in accuracy with a higher integration of Sentinel data. And yeah, I'll just leave some contacts for you, and feel free to reach out to us if you're interested. Thank you.
Thank you very much, Olivia, for that presentation and highlighting the role of technologies in food security. I'm particularly impressed by the use of the technologies that you've put in place. If I then go to our next speaker, who's Mashoud, who will speak about AMCO's Pan-African Groundwater Program and how it's addressing food security. Just a reminder that it's being translated, so just be mindful of that fact.
Yeah, thank you, the organizer, and appreciate the time given to us. I'm talking on behalf of the AMCO, trying to present about our flagship program called APAGROW. This is our groundwater program and how we are using this groundwater program to address the issue of food security. As a form of preamble, we look at it, what are the three critical elements of sustainable life and development? Number one, water is the first item, and water is life. The second item, food. Food is needed for sustenance of life. The third item, clean energy, and clean energy is needed to drive water and food security. The above three scenario of the element that sustain life and development is an indication of the fact that water, and indeed groundwater, is central to overall sustainable development. And we can see the justification of this in the fact that at least 6 of the key SDG are related to human survival, and they are directly dependent on SDG 6. So therefore, addressing water security, we address development and the survival of human beings in terms of food security and energy sufficiency. Now, within this arrangement, we can look at the nexus of the water, food, and energy, which the last speaker have briefly mentioned about. I don't need to waste much time on this slide, but rather than to say that you have your water security, which will give us food security. And if to attain water security and food security, we definitely need energy, sustainable, renewable energy. And that is why looking at these three elements of water, food, energy, one will wonder where is the air? Deliberately, I did not list air as this because if we don't have sustainable energy, if you don't have renewable energy, we will end up polluting our environment and the air. So the God-given air will be polluted, and the human being and the totality of the environment will be at the risk. And that is why looking at the water security, food security, energy security, we realize that human and the environment are the central focus of that nexus. So while we are looking for the water security, food security, and energy, the focus is the human and the totality of the environment. Then why water security matter? 5 key aspects of life is dependent on water, and that is why water security matters most. Number 1, productive economy. You cannot achieve productive economy without having a sustainable livelihood, which water security will provide. Without water, we can't have sustainable livelihood. We can't foster economic growth, and we cannot have economic empowerment of the population. Water is life. The second one is healthy living, of course. A society depends on water for human survival, and without enough clean water, there cannot be what? There cannot be sanitation services. So good sanitation services lead to healthy living. Water is key in this area too. Ecosystem. The ecosystem, which is the totality of the other environment apart from human, also need water for sustainability. Without water, many livelihood and resources will be endangered. So other bio-resources will be endangered without water. So that is why water is also needed for ecosystem. Also, livelihood in general. Water is essential for securing necessities such as agriculture, energy production, transportation in some cases, and not to sustain human life. So we need water in all these aspects. And finally, disaster risk reduction. If we ensure promoting stability and prevent conflict through water security and resilience to foreseeable unpredictable shock, definitely will prevent disaster in the future. So having to deal with water to assess the possible shock and the resilience of water will also help us to reduce disaster. So within this framework, Upper Group is an AMCO flagship program that is aimed at enhancing water and food security in Africa through sustainable groundwater development. Now, Upper Group, which is a flagship program of AMCO, what does it do? What do we with? How do we show the water and food security through AMCO? Arising from those key statements that we mentioned initially, water security within the framework of AMCO mandate is that AMCO is to support member states to develop, manage, utilize water resources to ensure water, food, and energy security. That means it's all encompassing. We are not looking at water in terms of sanitation and domestic use alone. Rather, we are looking at water also with respect to food and energy security in Africa. And within that framework, AMCO recognized and identify groundwater as one of the priority intervention areas in its strategic plan. It was on this basis that Upper Group as a flagship program was envisioned, and this program was launched a year ago. So the Upper Group principal aim is to leverage on science and to reassert to influence groundwater policies practice in Africa. Hitherto, when you talk of water, little is known about groundwater by the policymaker. So what we are trying to do at AMCO level is to see how we will use science, leverage on science and data to influence groundwater policy and practice at the highest governance level. And the goals are to promote sustainable management and utilization of groundwater resources for water security and resilience. You want to promote appropriate technologies and practice in groundwater development and management. And of course, we want to promote and improve policy practice of groundwater for better life and livelihood, while at the same time ensuring that there is knowledge sharing among the member states. So within this framework, AMCO operational strategy rely on 3 key thematic areas: policy and institutional system. Strengthen. We want to strengthen policy and institutional system within the African continent with respect to groundwater utilization and management. The other aspect is to also help to identify tools and means of technical solution, like country support tools, where we can identify appropriate solution and technology that we can use in groundwater exploration and groundwater development. Of course, the key aspect of our mind of this thematic tripod is capacity building. Capacity building towards sustainable groundwater management. This is a very key aspect that AMCO is envisioned to do so that we can impact through upper group the member states. And within this framework of the tripod, we have 6 thematic working areas as the operational strategy of upper group. Number 1, policy governance strengthening. 2, country support tools, management tool regarding groundwater, capacity strengthening and professional drilling technology. Then groundwater knowledge hub, where we want to create a knowledge hub, knowledge management, information sharing hub. So AMCO is to see itself through the upper group, a repository of all groundwater knowledge and information in Africa for sharing and dissemination among member states. Of course, the key aspect of our task is also about resource assessment. We are talking about groundwater management, whatever. All these things we are talking about, the key is the resource itself. How much do we understand about the aquifer assessment itself? What are the volumes of water? What are the recharge dynamics? These are areas that a lot of data are still missing in African context. And that resource assessment, aquifer mapping, especially within the transboundary aquifer zone, is also a key aspect. And finally, the key target area is also to see how do we encourage public finance in groundwater sector. Either through large irrigation projects relying on surface dams are there, but smallholders agriculture are using a lot of groundwater in some area. How much of private and public finance is going to this sector? So one of the agenda is to see how APAGRO will encourage and drive policy in increasing public finance in groundwater sector. And looking at it from the other perspective, to look at what are the challenges and what are the food security challenges that we have relating to water and food security in Africa. We know that water security for Africa presents challenge due to increasing pressure on water resources, population growth, economic growth and urbanization, land use changes, climate change. These are critical elements that serves as challenges to groundwater and water resources development in Africa in general. And when you look at the tripod of the water, food, energy security, you look at the diagram here, where you have, within this context of this tripod, we have to contend with the urbanization influencing this tripod. We have to contend with the economic growth, climate change, population growth. These are the factors that influence. And if you are able to manage all these factors very well, we will ensure a focused water management system. And that focused water management system will drive water security. And by driving water security, we will be able to get water for domestic use, water for ecosystem, water for environment to protect climate change, against climate change, and water for development activities. And these are the focal area of groundwater program of AMCO. Now, why water for food security. Water security for food security. Defining water security, we can summarize the fact that access to water in adequate quantity, acceptable quality, and the accessible source. The source has to be accessible, it has to be of adequate quantity, and it has to be of acceptable quality. If we don't have these three components, it means getting sustainable management will be problematic. And if we're able to get those sustainable management by providing water in acceptable quality, quantity, and accessible source, then we will ensure productive environment, healthy society, sustainable ecosystem, and we'll be able to ensure resilient environment that will be able to face the challenges of climate change. Then, moving forward again, why water security for food? If you look at the maps that we have two maps presented at this point. And from these two maps, it is clear the similarity and the overlap between Global Hunger Index 2020, and then you have the Global Food Security Index. You can realize that the bulk of the African continent have poor showing in terms of Global Food Security Index, which translates to Global Hunger Index. And within this context, how do we move out of this scenario without increasing food production? It's not possible. We need food production. And to increase food production, to move out of this scenario, we need secured water. And that is why water security matters in attaining food security. More so when you realize that 64% of the African rely on water that is limited and highly variable. 25% of African population suffer from water stress. And also nearly 13% of the population of Africa experiences drought-related stress once each generation. So based on all this, we can see the need and why water security is very key for food security. But then, why are we focusing on groundwater? Three key reasons. Number one, the volume of groundwater stored in Africa is estimated to be 20 times more than what we have in our freshwater lakes and rivers. So that means we have large potential in terms of the available groundwater resources that we can use. At the same time, we need to feed 320 million people in Africa that lack access to safe water. They need water. And groundwater will be a reliable source to meet their demand, especially in the face of the climate change. Groundwater is also a key resource to climate change resilience, as I mentioned, environmental protection, tackling poverty. So looking at this scenario, it means the potential for groundwater to meet the climate change in terms of access to water, to provide water for agriculture, irrigation is very high. The fact that we have more than 20 times of what we have in our surface water and lakes and rivers, which are really being affected by climate change. So groundwater provides that potential for water security. It provides that potential for food security because smallholders agriculture can use and livestock production can easily use this groundwater system at a cheaper rate. Cheaper source of water for smallholder irrigation in the multitudes of rural areas that constitute major part of Africa. In terms of water supply, it provides cheap off-grid source of water. Of course, safe water in terms of the quality for health. Groundwater is generally protected and is generally of higher quality, good natural quality in most cases with little or no treatment. And of course, in terms of the resilience, as I mentioned, groundwater is buffered against the impact of climate change compared to surface water. Based on this, we realize that there is high potential for groundwater, and tapping into this potential will greatly support food security in Africa. So groundwater as a key to food security, as I mentioned again, what is the way forward in terms of conclusion and recommendation? To feed the appropriate 1.8 billion people in Africa by 2050, agricultural water allocation must be more efficient, and deployment of groundwater must be a key source. Challenges faced by water resources and prevailing food situation are recognized as a global problem, especially in sub-Saharan Africa. There is the need for shared understanding of the problem. There must be shared understanding of the problem in a way that the consequences, the solution that we are going to, and the trade-off, we must to achieve that objective. So the policymakers must take the lead. There is the need to develop common awareness and understanding among the policymaker, and that will help the future decision maker in Africa on the significance of groundwater in food security. Appropriate action must also be taken on economic policy and trade investment. So there must be investment into this infrastructure in groundwater and so on, so that we can have a sustainable deployment of groundwater. Of course, African countries are to develop consistent, comprehensive water and food policy to promote equitable trade, expand water storage, and improve water quality. That is the only way we can deploy this water in food production. Finally, moving forward, what are the policy recommendations that we can? Secured water rights. There must be an avenue to secure water rights for farmers and gender involvement. Incentive for efficient water use. We must have a way of encouraging the incentive, encouraging and providing incentive. For example, payment for environmental service, watershed management, and so on. We must encourage best practices in using adaptable technology. There must be a compensatory income or input support for smallholders farmers to encourage them to deploy groundwater use. Increase investment, of course, I've mentioned that before, and we need a public-private partnership using satellite-based remote sensing, groundwater mapping, which the last speaker already mentioned such technology as available. Then tools for stakeholders' involvement. We must increase the awareness and the involvement of stakeholders. Farmers-oriented program that will be driven by the farmers in the rural area will increase the food production. And finally, I'll look at it from the angle that what AMCO is contributing. Through our upper group program, we are contributing capacity buildings and collaboration, institutional policy framework strengthening, infrastructural financing. These are the focal areas that we are trying to improve the groundwater resources utilization and management in Africa. And
Thank you. Thank you, Mashoud. We need to finalize now.
Yeah. Finally, this is the last slide. Finally, we realize that within this framework, capacity is one of our strong elements, that there is need for capacity development. Effective human capacity and better and efficient institutions are key. And that is why within the framework of AMCO, we have capacity development and knowledge management as one of our key agenda in driving groundwater knowledge sharing, knowledge management, and effective utilization and sustainable development among African states. So with that, I thank all of you for your attention. I thank some of our partners who have supported in the development of the Upper Group program. The key one, BGS, BGR, UNESCO, IHP, and IMI, they are key partners that help to shape the Upper Group program for the AMCO. We thank you for your support. Thanks so much for your attention.
Thank you, Mashoud, for that presentation. I will immediately go to Marcus Binion, who will make a presentation on water for food in Central and southern Angola, the role of groundwater. Marcus, just be mindful of that translation is taking place. So when you speak, don't speak too fast. Thank you very much, Marcus. Can I hand over to you?
Yes, thank you. Let me share the screen. It's coming up. Maybe. Can you see it?
I can see the screen and I hear you well. Thank you, Marcus.
Okay. Yes, thank you so much. Yes, after this presentation that shows the linkages between water security and food security at the level of the African continent, I would like to present a case study about the connection between water and food in central and southern Angola. So it's a case study conducted by the World Bank. My name is Marcus Wijnen. Till a year ago, I was the groundwater focal point at the World Bank Water Practice in Washington. And this study has been conducted with a team of experts from basically focusing on drought vulnerability, water resources issues, and water harvesting solutions. Now I'm struggling with moving the page. Now I have shared the screen. I'm not sure how this works. Let me, okay, here we are. So these are the contents of my brief presentation. So we will look quickly at the impacts of the drought in South and Central Angola, the identification of possible infrastructure solutions, including groundwater, and then I will look at one example that was part of the study, focusing on the challenges specifically in the Kuvalai Basin shared by Angola and Namibia. So as a brief background, the region was hit by a long and severe drought that basically continued almost without interruption from 2012 till 2019. And the impacts of that drought were felt deeply, also because already we have structural problems in water supply and vulnerability of the existing water supply system. So, as I mentioned, the work here is part of a larger study that was conducted between April 2019 and 20 that aimed to find suitable solutions that would be resilient to the current droughts. Out of this full study, I will focus on the last two aspects, which would be the assessment of the water resources available to be mobilized for food and water supply, and the nature-based solutions that were identified to provide that kind of water security. So just in brief on the impacts of the drought, the agro-husbandry is the main economic activity in South Angola. And due to the dynamics of the transhumans, this poses particular challenges to building, well, first of all, water supply system in general, because of the moving pressures, the seasonal fluctuation of the demand, but particularly under drought conditions when the normal transhumans patterns are disrupted. So as we can see on the right, the drought has multiple impacts at all levels of the society, but agriculture and livestock in particular were the main sectors hit in South Angola. Just to have an idea about the level of the impact, we see on the upper figures in blue and red, the rainfall anomalies compared to the average of the last 4 years. So red being lower than average. And so we see that especially in the last year, in the right figure, the southern part of South Angola was severely hit. And this is translated immediately in the lower range of figures shows the NDVI for those years, basically the anomaly of the NDVI compared to the average NDVI for the region. And we see immediate strong impacts on the availability of fodder. So based on the fodder availability, the cattle, the herders will move to different areas. Added to the pressure is that in Namibia, the drought was also hitting hard, and many herders from Namibia also ventured into Angola to save their cattle. So what we see is basically a rapidly changing pressure on water points. It is one of the main causes of failure of water points, is that the water points would be able to function under normal conditions, but they fail when the pressure rapidly increases during droughts. So groundwater is currently being used in South Angola for irrigation as well, but mainly in coastal basins in the Namibia province. And even here we see also that there is a strong fluctuation of the irrigation activity depending on the drought conditions. So in drought years, the small aquifers that are being used allow to irrigate much smaller quantities of land. So here as well, we see an immediate connection between the pressure on the resource and the prevailing drought conditions. So the case study I will briefly present in this talk is basically focusing on one part of the south. It's the Kuvelai Basin. And as we see on the figure on the right, in the left part of the basin, we have an inland delta. It's a closed basin, the Kuvelai Basin. It's basically flowing towards Etosha Pan, but rarely overflows. And so we have in this inland delta flat topography with many channels. So there is seasonally, we can see on the picture, an abundance of surface water. The region floods to a large extent. But as we can see on the graph, rainfall patterns are highly seasonal. And typically there are 5 months with absolutely no rainfall. And so the challenge will be in this area with flat topography, with very limited possibility to have dams or surface water storage, to provide a secure water source for agriculture and also for human consumption. Typically, in the southern part of Angola, people use water harvesting structures they call chimpacas. They're basically small tanks that capture the water from a small impluvium, a small flat area, a small piece of a channel. And typically this is sufficient to feed a small population of a few households and their cattle through an average rainfall year. We also see already in the same Kuvelai Basin that groundwater is used, but at a limited scale. Most of the groundwater use, as we see on the pictures on the left, are through artisanal hand-dug wells or large open wells that tap perched aquifers, usually with a very low yield and also a low overall capacity. So groundwater is used for individual supply of households or small groups of households. We do have a number of boreholes in the region, hand pumps or solar powered pumps, but the groundwater potential in the region is generally considered as poor. And I think it's important to mention that what is really poor is basically the data availability. The knowledge about groundwater resources is extremely limited. There are no records of existing boreholes. There are no records of the functioning of the boreholes. There are no hydrogeological data that are structurally collected and monitored. So we are basically operating in a region where the knowledge of the groundwater is extremely low, and this results in extremely high cost of boreholes because typically boreholes have a very high failure rate. The drilling has a very high failure rate, and then once boreholes exist, their lifetime is often limited because of the absence of maintenance mechanisms. As part of the we did also a field survey, basically with multiple objectives. It was to check possibilities to improve the design of the water harvesting structures, verify the surface geological conditions in absence of existing data, but also a survey of existing water points to basically evaluate the groundwater potential and also the groundwater quality variations. On the picture to the right, we see the Kuvelai Basin. It's, as I said, a landlocked basin. And so in absence of monitoring data on runoff, as well as on groundwater, we have chosen a water balance approach to basically evaluate the availability of water resources. And the water balance approach is facilitated by the fact that the basin is a closed basin, so we also have a closed water balance. Without going into too much detail, basically the starting point of the water balance was the extensive use of remotely sensed data, in this case of rainfall and also of actual evapotranspiration, where we have already like a 20-year record that can be used. And for the 3 subbasins that were delineated, we have calculated for the last 20 years, actually the excess of rainfall during the wet season and the deficit of the rainfall minus the ET during the dry season, and basically to understand the dynamics of the basin. So what we learn is that in this basin, we do have mostly limestone substratum, which is uniform across the basin, which is quite impervious and has a low groundwater potential in general. And on top of it, we find a very shallow, maximum 3 meters thick sedimentary cover, which basically provides a very small reservoir for storing infiltration water. So what we see in the dynamics of the basin, on the graphs on the top, we can look at one of the graphs because basically there are 3 graphs for the 3 subbasins, but in blue we see the rainfall, and in green the actual evapotranspiration average, calculated for the surface of the basin. Then in orange we see basically the deficit or the excess. So the patterns are quite similar. We see basically during the rainy season excess rainfall. So it's basically water accumulating in the basin because no water is leaving the basin. And then during the dry season, the same water that is stored in the basin, in channels, in the soils, in vegetation, is taken back. So if we calculate the water balances for each of the basins, we basically see that almost 90% of the excess rainfall in the rainy season is taken back by evapotranspiration in the following dry season. And this is for an average year of rainfall. We have limited information about the recharge, but we used information from hydrogeological maps to basically have a starting value for our water balance calculations. Again, without going too much in detail, so we have established water balances for the subbasins. And what is important to mention is that we can see that the groundwater recharge is evaluated at around 3% of the annual rainfall in an average year, but that the harvesting potential is it's in the blue boxes, the highlighted line. The harvesting potential is very substantial. So it means that at least seasonally, a lot of surface water is available. Based on this, we have evaluated that in the Angolan part of the Kuvelai Basin, there would be a potential to harvest up to 36 million cubic meters per year, which is more than 10 times the amount that is currently harvested. So it seems that on average, based on the average rainfall, there is a substantial potential for surface water harvesting. But if we take into account the climate variability, which is very high, and we calculate basically water balances for years with below average rainfall, then we see on this graph that quickly the evapotranspiration actually measured in the basin in those dry years exceeds the excess rainfall of the previous season. So we have a dynamics of a basin where a lot of surface water is available, but the potential to harvest that surface water quickly evaporates when we have years of drought. So we have a difficult situation where the surface water is not available, obviously, in the years we most need it. And this greatly reduces the potential for surface water harvesting. We see in the small box in the bottom right that in a year with intensive rainfall deficit, as we have seen in the 2018-2019 year, the surface water harvesting potential quickly is reduced to less than 30% of the average. So with this knowledge in mind, the project has then evaluated all the possible infrastructure solutions compatible with the climatic conditions in South Angola, and also with the fact that we are talking about rural water supply interventions. So this is not for small cities or even larger cities where we have different kinds of options. So the infrastructure solutions are mainly conditioned by the availability of the water resource, whether it's groundwater or surface water, and then subsequently on the demand and the volume of water that we would like to supply securely. Again, without mentioning all of the details, basically, out of this decision tree, groundwater very clearly comes out as the preferred water supply options. And we have already heard in previous talks the advantages of groundwater. It's less vulnerable to the short-term climatic variations. It's largely protected from the anthropogenic pollutions. So it has a lot of advantages. But as we saw in the Kuvalai Basin, the shallow groundwater resources that are being tapped have a very limited potential. And we have so little information about the deep groundwater resources. So even if we would like to expand the groundwater use, this will require intensive studies and like changing of practices in groundwater monitoring, in systematically collecting groundwater, quality and quantity data, in improving the drilling practices. And I mean, these are issues we see obviously in many countries, but in this region, it's particularly critical. So according to reports from Namibia, where more groundwater information is available, there is also the presence of a deeper aquifer below the Kuvalai Basin. But in Angola, there is no borehole tapping at aquifer. So today, there's simply no information available that would allow us to decide that that would be a valuable option for future infrastructure. In addition to the resource limitations, we also have a problem of many management issues, and I think this is valid for other countries too, but food security and water security, they are also partly a man-made problem in the sense that it's the lack of investments, but also lack of maintenance mechanisms. And in the case of Angola, of the existing boreholes, almost half of the boreholes is out of order, simply because of failure to repair within a decent period of time. Now, coming back to the possibility to use surface water as an alternative source for supplying water to cattle and to human populations, we have seen that the surface water by far is the largest confirmed water resource in the basin. But here also we have very particular limitations. First of all, the same water points are used for animal and human consumption, which creates a great public health hazard. And so we can find solutions to for this by, for example, building separate water harvesting structures for human and cattle with a different design. They can even be optimized. But then if we look at the design of those structures, there's just one graph. It's a small summary of an extensive part of the study. But if we look at the two graphs at the right, the top graph is basically a graph that shows in an average season, we see the number of days from the start of the rainy season, the time it takes, depending on the design of the chimpaka or the cistern, the time it takes to fill up. And so we see that basically increasing the size of chimpakas is not a solution, simply because it will be very difficult for them to fill up during an average year. And if we then look at the lower graph, it's for the same design characteristics of the water harvesting structures, we see that they take much more time to fill up in a dry year, and most of the structures with optimized design characteristics, they fail to fill up in a drought year. So we have a situation where in the end, there's no single water resource that can provide water security. So we need a mix of solutions. We know that surface water is the single largest available water resource in the basin. So the harvesting can be expanded. And this could provide the bulk of the animal water demand, which is much higher as in many places as the human water demand. And it could also provide at least part of the human water demand. And so there are possibilities. We have studied the possibilities to build a different type of surface water harvesting structures by making them deeper, but this quickly increases the cost considerably, because we have the limestone rock at the shallow depth. And in the end,
Marcus, can we conclude now, please?
Yes, this is the last slide. Time.
Yeah.
Yes. So in the end, the situation is that even though groundwater potential is limited, still groundwater is basically the only resource that can provide the water security needed to build resilience against occurring droughts. So there is one resource that is available for most of the water supply, the water harvesting, in average years. And then we will need a system where strategically located wells complement the water supply to provide water security in the driest years. And so this needs then to be matched to the current transhuman routes. And we will need information systems for the herders to be guided to the right water points. So in this case, groundwater is already the strategic resource without which we cannot provide water security. And it's recommended to obviously to conduct further studies, because there may be the groundwater potential may be larger at greater depth, and this is yet to be confirmed. So I would like to leave it here as an example of Angola, and back to you.
Thank you, Marcus, and thank you for that presentation and the case study that you presented. Can I immediately go to Barbara to talk about recognizing customary water tenure in groundwater development and regulation to achieve the Sustainable Development Goals in Africa? Barbara, over to you. Thank you very much. I see your screen.
Okay. Thanks, Kevin. Thanks, organizers. Thanks, Karen, as well, for focusing now on the human resources, as Moshood mentioned, an enormous asset, in addition to the water and the energy. And yeah, talk about 3 points, basically. starting with the infrastructure here, like the woman who is carrying the yellow engine, as they call it in Zambia, the need, of course, to enhance the technologies, but also mentioning already that the seller supply like this is undertaken by many more peoples and covering a much larger area than public schemes, both domestic wash and irrigation. I come back on that. So starting with the infrastructure, but moving to the community. The women that are there, but also the land which is held by the community. And then for the infrastructure, moving to the community, but also for the informal and formal water rights that you mentioned. Okay, now. Yeah.
Barbara, can you put it into presentation mode?
Let me do that. Yeah.
Thank you.
Okay.
Yeah, perfect. Thank you very much.
Okay. So basically talking about customary water tenure. So the relationships between people with regards to the water resource, quite broad, as FAO has been defining it for many decades already. Community, we focusing on rural areas who share the common interest in the territory and the resources, water and other resources related to the territory, including water. So then we get the definition of customary or community-based water tenure, the group held rights that are very dynamic, that change quite a bit, certainly with new technologies, with energy improvements, etc., to manage together the water resources. And we talk about large areas. If we compare it with land tenure, groundwater is under our feet. Land tenure can cover up to almost all rural land. Customary tenure is almost all rural land in countries like Zambia and Tanzania. So the 3 points, what can we learn from participatory approaches, really taking the human resource as entry point at the infrastructure scale, individual infrastructure, but also infrastructure at community scale. And then the sharing of water resources, the regulation, the trade-offs, the allocation, which is an issue at community scale. And of course, depending on the aquifers, also the higher scales, especially government. So the first point on infrastructure, what we see in our work is that people, they use infrastructure for as many uses as they need. The drinking, the other domestic uses, livestock, crops, fish, crafts, enterprise, cultural, ceremonial uses that meet their multifaceted livelihoods. And here, especially around homesteads, people have many needs. Women and men have many needs, and they use very cleverly for as many needs as possible. And also at community level, they combine the multiple sources, the surface, the groundwater sources, the wetlands, the conjunctive management of their multiple sources. Basically, at community level, we talk about local integrated water resource management. And multipurpose infrastructure is a local practice which makes all sense. It's also already raised the issue of water quality in the, what I then call the productive domestic water nexus. We tend to talk about wash, water for drinking, domestic uses on the one hand, and then water for productive uses at the other hand, a sectoral approach. But for communities, water is water. And you need, for the same people, need the same water resources. But there is definitely, of course, the issue of clean water that needs to be clean for drinking. And here you see the example in one of the villages, Gamuela, where the upper part has been reserved to take water for domestic uses, and the downstream part is then used for by the animals. So there were and there are customary arrangements that satisfy the need for a bit of water that needs to be clean for drinking. And it is important then to keep those rules and arrangements throughout the modern times as well. Importantly, it's only 5 liters per person per day that needs to be clean for drinking water. So we don't need water for laundry, of drinking water quality, water for scrubbing floors, for drinking water quality. Fine, as was mentioned, groundwater is often already clean enough, but if it isn't, fluoride, arsenic, pollution, of course, then the wash sector is looking at point of use treatment just for the 5 liters per person per day that really needs to be clean. At the right side, you find an interesting driver to achieve the first SDG 6.1 for water for drinking and other domestic uses. Throughout Africa, we see that the multipurpose pumps enable irrigation, especially if there are markets, that's number 1. And then that gives the money for people to invest in the pump for self-supply, which then also helps to achieve the constitutional rights to water for drinking and domestic uses. So people's own investments in multipurpose infrastructure, if there are markets, if there is low-cost infrastructure, if there is cheap energy, helps to achieve the WASH goals as well. And for that, it's so important that women are not left behind in the capacity building, the training, the access to mechanized infrastructure. I'm now going to talk about this village, Hagumbu, in South Africa, where energy became available through electrification, and where many households then invested in their private household boreholes and started using the boreholes for multiple uses. At the moment that the municipal system collapsed and was replaced by a better one, everybody was dependent on the private borehole owners, and at community level now, moving to community level, we see a lot of sharing. And this is also work by my colleague Manuel Magombe, who then calculated exactly the amounts that were used. On the one hand, among the non-borehole owners, and on the other hand, among the borehole owners, and categorized the people depending on how they, on which water service level they met. So at the lowest, the lowest step of the water ladder, we found the households that had to walk to their neighbors to buy water. At the next level, we find households that made a connection between their neighbor's house, the borehole owner's house, and their own house. And a big jump was made by the borehole owners, but there we found some of them not happy with the storage. So the JoJo tanks, the plastic tanks at their households that enable 24/7 water availability for domestic uses especially, but it also helped to water the irrigation fields around the homestead once every 2 or 3 days. Storage came out as a very important aspect of people's perceived service level. And at the highest level, we found the borehole owners who had enough storage and were happy, and they just wanted to expand and have another borehole, especially at their distant fields. I won't go into the details of the graph here, but it shows, I think, above all, that even among the lowest step, the people at the households at the lowest step, they need water for their livestock as well. We found only 5% of all the households in the sample that only used water for domestic uses. So another point then for the importance of looking at the community is the design of any outside support. Here we see a case that would also be in Namibia of Angola, as we just heard. The pump has to be so deep that it has to be supported by the government, by the public sector. But even then, we found that if we do a really participatory approach, we are still working on that with the Water Research Commission and the African Development Bank. But by applying this participatory approach of any public service, we expect a much higher sustainability of the issues at stake. And as every planning process, we start by initiating committees, representation, diagnosing by the people. They have known their water resources and their infrastructure since time immemorial and have a lot to offer to share that understanding with any outsider. So, then also for the solutions, and here we talked about the smaller scale reticulation. Where are the taps going to be placed? Which households are able to manage a shared street tap? And that type of smaller scale technologies, the people know best how they can manage that. So they make designs, and of course the more sophisticated engineering expertise would make sure that the deep pump works. But they make the designs where they can. These are then the proposals to be approved by the financer, government, the banks, municipalities, NGOs, etc. And then also the implementation is done as much as possible by the people themselves. And we expect a much higher sustainability of this form of what we then call co-management. Government with the responsibility for a functioning borehole, and the community owning the borehole, but especially the reticulation and the smaller repairs, taking responsibility for the smaller repairs. So now I move to the third point, talking about the formal and the informal water rights that Moshood already mentioned. And then the question is really, why does hybrid water law, hybrid water tenure, why does community-based customary water tenure not even figure in our water laws? Why do we forget about it when we talk about rights? And here, our work or research with several of the listeners has really realized that we are still dealing in Africa with and other continents with a colonial legacy. In the sense that the current permit systems, in which the state is the custodian of water resources. That system was introduced by the colonial powers. And with a stroke of the pen, they just said all water resources are vested in His Majesty, the King of England or Portugal. So in the beginning, most surface water sources, but gradually also the groundwater resources. And by now, all water is seen as owned by the state. I come back to that. The colonial powers, they granted permits exclusively to the white settlers, and putting prior African water uses and water management arrangements, relegating that to a second-class status. Permits, as such, are useful because states get a lot of data and information about it. The problem is now that it then becomes the only right. And that is the post-independence, the problem that we see in many African countries, including SADC. The state is the custodian, and they have extended the permission of the obligation to apply for permits to all water users, except the very small ones. And without acknowledging all prior and rapidly developing water uses and water management arrangements, customary water tenure of all the centuries before, with a stroke of the pen, they criminalized especially the customary water users by saying you are unlawful because you need a permit. And at the same time, for example, the National Water Resources Strategy of South Africa in 2013 writes that the current permitting licensing processes are costly, lengthy, bureaucratic, and inaccessible to many South Africans. So on the one hand, the permit systems say you need a permit, millions of small-scale users, and at the other hand, they say, yeah, sorry, we can't process it through individual permits. The small-scale users for domestic uses, small-scale gardens, etc., they are exempted from that obligation, which means that they are completely invisible and that there is no way for them to claim their maybe age-old water uses, the prior water uses, vis-a-vis permit holders. And again, customary water law is overridden. So that's why this notion of hybrid water law is now being discussed. Basically, it compares the number of users and the volumes of water used in the green and the blue triangle. Huge inequalities, essentially a few large-scale users, maybe the flower companies in Ethiopia, use a lot of water compared to the millions of small-scale users, the majority of the rural population. So then the discussion now is how to target the permits to the few big users that needs to be targeted and regulated, but how to find other tools for the water users that are already governed by customary water tenure. And then I conclude with all the issues about polycentric groundwater governance, in fact, that does recognize the sharing arrangements that already exist. And you have been discussing all these issues already here, and we will continue tomorrow. Number one remains the development of infrastructure, leaving no one behind. Everybody needs access to water for domestic uses, affordable and near the homestead. But under competition, and we can anticipate that and make sure that even the public services, the infrastructure development is as equitable as possible already now. If there is competition, there are all these issues that we heard also this afternoon about knowledge about the resource, but also tapping people's own knowledge. The whole issues we just mentioned as well, the augmentation of the supply. But when we get into really asking who gets water first, again, communities have their own rules already. But then for the governments, the value to align with the overall goals of food security for everybody, water security for everybody, sometimes the constitutional right to water would really be to start bottom up with a core minimum of rights to water for domestic uses, but also water that meets the right to food security, nutrition, etc., or summarized enough for all forever.
Thank you, Barbara. We have to stop now. Thank you very much for this thought-provoking question. Can I just ask all the presenters to put their videos on so that we can see everybody? Apologies, Program Director. I've not been a good chairman in terms of time management. If you just allow us maybe a few to go over a couple of minutes in terms of questions that people may have to ask. I'll just go to the question and answer box. There's a question or a couple of questions from Raquel Suso. He or she, I'm not sure, says, I have a couple of general comment questions for us all. It reads, Sub-Saharan Africa is rich in highly nutritional foods, natural growing in the continent. The question basically is, has these crops been mapped, whether it's natural or traditional growing in countries? And then I think it talks also about permaculture and agroforestry systems. And maybe I can then ask maybe Karen to talk around some of the issues around the type of crops and the productivity of crops and whether that is, has been already mapped out and so forth. Karen?
Thank you, Kevin. I think the issue of nutrition, first of all, is very critical. We sometimes forget about it and we only look at the food productions in terms of mass or kilojoule or something, but the nutritional value is critical. So thanks for bringing up that issue. In terms of mapping various crops and aspects of nutrition, I think we are probably not quite there yet. I know that there's some global mapping being done in terms of, I think it's 42 crops that do include some of these maybe smaller crops or indigenous crops. But I'm not sure if there's been any serious significant like differentiation in terms of nutritional value and so on. So I think the question is valid and something to look further into. Thank you.
Thank you, Karen. Maybe to go over to Olivia around the next question, how to engage in new practices and technologies addressing water, energy, and food security. So I think it relates perhaps to a whole-scale adoption of new practices and technologies, and what perhaps the barriers are and how we can overcome those barriers.
Yeah, thank you. I think that's a very relevant question. We learned in our project that these technologies need very much to be context specific. Therefore, the first step is always a thorough understanding of the needs and what type of technologies work and in which situation. So we range, for example, from use of smartphones for advisory services to text message or voice messages on very old phones, for example. So that in this, speaking about this type of technologies, So yeah, we should be aware of the fact that that innovation can take many different forms, and what can be an innovative approach in one place doesn't work in others. So understanding what are really the needs and co-design and co-development of such technology and solutions is the way forward. Thanks.
Thank you, Olivia, for that. Maybe if I can maybe go to Mashoud just to ask the question around policy uptake. We sometimes know what needs to be done, but how are we going to inculcate these kind of messages into African around the role of groundwater in food security, the role of groundwater in energy security? How are we going to kind of make that jump, assuming that we haven't made that jump already?
Thank you. I think it's two ways. The first aspect is the fact that AMCO has that political leverage to leverage with the highest political levels in the African continent and to drive the policy. And that is what APA Group is trying to achieve by making sure that groundwater is recognized at the highest level of policy decision when it has to relate to water resources development and management. That is the one aspect. But the second aspect is taking it on board, whether we have already done that, is to look at the fact that how do we increase investment in this sector? If the policy is driven and there is no political will to invest in groundwater infrastructure, new technology of solar power, whatever, so that this smallholders farmer will be able to benefit. Relying so much on these big irrigation projects may not necessarily lead to increase in agricultural production, because the bulk of the farmers are in the rural community. And that is why groundwater is going to be the key. And while we are driving the policy at the AMCO level to make sure that the political and decision makers recognize the significance of water in agricultural production, I think that political will to increase investment, change the policy in a way that will make the access to water, land right, and related constraint easy for the rural farmer. I think those are the other aspects that are critical. And I think we need a lot to do. I think the political will and the financial commitment is what is needed to drive that, so that we can move ahead like the Asian countries have done in terms of groundwater irrigation. So I think we are still a bit behind. Thank you.
Thank you, Mashoud. Maybe then to go over to Marcus, maybe to ask this question within your broader your broader role within groundwater governance and the work that you've done it and now relating back to the case study that you've done. So the whole question of how do we trigger groundwater use for agricultural development, to go into the boom phase, but at the same time, how do we then mitigate the bust phase, so to speak, that the other Asian countries has, or as examples in Asia and other countries has shown. So the context is, how do we trigger that kind of development, but at the same time, mitigate the bad practices? Marcus? Marcus left us. Karen, can I maybe ask you that question to put you on the spot?
Yeah, that is really putting me on the spot, Kevin, because that's one of the key issues, I think, with the development of groundwater. I think key to sustainable groundwater will be awareness and knowledge and investments, like Moshood was mentioning. If we just leave it to the private sector and to the economic development and so on, we will probably see a boom and bust cycle, as we've seen other places. But if we have intelligent, approaches, if we do work with the communities, and if we work with the necessary technologies that can also give us feedback on the resource availability and so on, and we do include some criteria, if you like, in terms of environmental sustainability. We provide some economic incentives maybe to the farmers and to other users that will provide, that kind of a limitation to the use. I think that is the only way forward. But we need to educate everybody about groundwater and the risks, and then take that into account. And I think it's both at the higher level, like formal education. It's the political level with awareness and buy-in from the politicians and policymakers, but it's also in at the community level, as Barbara was talking about, where I think users very quickly identify issues and will have to adapt, to any negative trends to the resource, because it's the bread and butter and basic question of survival. Thanks.
Yeah, thank you very much for taking that question. Maybe then lastly to Barbara, you've really put in my mind, certainly put forward some thought provoking ideas and concepts, but how do we start actualizing some of those concepts? As you well know, legislative reform and water reform takes quite takes decades to take place. So what is the kind of short and intermediate steps that are required to kind of start changing our mindsets in terms of how we view water allocation specifically?
Thank you. Kenya is already doing it in the sense of categorizing their water users according to the small users, the A, B, C, D. The A is decentralized, is a matter of registration. So not a whole process, but of course, government needs to know about who is using water. So they have a light procedure to register and make small users visible. And then the B and the C becomes the bigger users, and the D users are then also the transboundary large-scale users. So that is one way to they have the same law as South Africa, as most countries, but that's something that each country can immediately do as a use of the existing tools to realize, what is the purpose of permit systems at the moment. And in South Africa, we are now working on hybrid water law in the Inkomati basin, which is already more decentralized, to use the general authorization, because South Africa has a general authorization that also allows a lot of flexibility on the threshold below and above which you regulate. So, and at the same time, parallel to that, much more openness, study of what customary water tenure since time immemorial entails, and how it adjusts to the very rapidly changing environment.
Thank you, Barbara. It's good to know that there's already examples and that it can be fast-tracked, so to speak. I don't see any other questions. I've just got an anonymous attendee that's saying, can't all presenters perhaps send us website links where we can literally acquire all the information thus far for reading interest. I'm sure the presentations will be made available and people probably can get information through that process. Program Director, I don't see any other questions. Can I just then thank the people for the presenters for their very enlightening presentations. Mr. Program Director, you probably won't use me as a chairperson anymore, but I don't mind. But I think the presentations has been extremely useful and insightful. So thank you very much to them.
Thank you so much, Kevin. Thank you so much. You know, it has really been an exciting afternoon. It has gone very, very fast. And, you know, the presentations were so exciting. You know, we are really happy, you know, with what has gone on. And would like to apologize, you know, to our attendees, you know, for overrunning our time. But I think it was worth it. It was really worth it because we have really been able to get answers, you know, to that question. Groundwater for what? Now we know we need to produce our own food. We also know that we need to use groundwater, you know, for irrigation. So it has really been good. So I'd like to give you a big hand, Kevin, you know, for sharing this last session, and also to the presenters. Thank you so much. It has been a great day, you know, having you around and sharing your knowledge with us. It is great. I'd like to thank the presenters for this afternoon, for this last session. And I would also like to thank those presenters that did present early in the morning and throughout the whole day. The chairpersons, you know, who have handled the sessions, our rapporteurs, you know, thank you very much. I think the sessions today have really been very interesting and taxing. I would like to also thank the technical team who have made this conference today to be what it did. You know, we had no technical issues, and that was quite exciting as well. I know that with virtual meetings, you know, it's going to be the new normal, but I, however, you know, miss, you know, the one-to-one interactions that we normally have, you know, at these conferences. But we then look forward, you know, to the fourth SADC conference next year that perhaps, you know, we'll be able to meet and interact as we normally do. I would like to just make one announcement that if you look at our program tomorrow, please don't go away. Tomorrow, can you join us? We are going to continue with our program tomorrow. And the first presentation is going to be at 8:30. So I was going to suggest that let us meet at 8:20 so that we can do some housekeeping issues. And then thereafter, we have our first presentation at exactly 8:30 tomorrow morning. So with those few words, colleagues, I would like to say, stay safe. We've done our part today, and I would like to thank you so much. And please join us tomorrow for the last session of this third SADC Groundwater Conference.